Okay, so good morning, everybody. This is our second day, and the agenda is here. We might try to do certain things faster if the talks end up being shorter. So first, Christos is going to talk about the demo today, and also Evangelos is a student. Okay. And then maybe we will skip the guest talk and have maybe half an hour lead in traveling to Silver Lake, and then do the demo, come back, eat, and then we have a few afternoon sessions. Okay, so Christo, are you ready to present?
Okay. Great. So, thank you again for being here. Day number 2 has the theme of robust obstacle avoidance. And before we jump into discussing what we're going to be seeing today, I just want to make like a precursor, which is a small recap of what happened yesterday. So obviously, we couldn't upload the data there in the field, show you everything, go through everything, and we couldn't do live data really because the way that the system is configured, the wireless communications are not as high bandwidth as we would have liked in order to have live data streaming. So we just pulled all the data and have some indicative images of what was happening on the actual aircraft, and they are here to briefly present today. So onboard imagery of the actual test. At the moment where it takes off, it's a little bit, I don't know if I have control over this. Doesn't, oh, give me just a second. Perhaps like that. Yes. All right. That's much better. All right. So we started off with ferrying away from the launch location, and at some point around the takeoff where it got initiated, you can see we are right here, but you can see some of the crowd didn't get very well captured by the camera and everything, and we can also see like the cars parked out there. So we are all around the area at the time. So the takeoff, the fixed-wing transition, everything that you saw there from the outside, and some detections as they lake bed detections as they happen on the onboard camera. What you see here is actually a minor blemish of what the operation entails when you take off from the water. You can see some water that's on the lens, and it's a little bit blurrier than we would have liked to. These images that you saw here yesterday before we went out into the site correspond to a takeoff from dry land, so the lens was pretty great and everything. So we had to actually train a network just a little bit better to encompass cases wherever there's a potential lens blur because of condensation that can happen on the lens, just to make sure that we would have adequate detections for the entire mission. The final outcomes, of course, that at some point during the execution here, we will see that as it's doing the loitering cycles, it cuts to the right. This is the point where we have the simulated fault that happened somewhere around here. Yes, this is cutting to the right because it responds to the simulated fault and does the final landing sequence to one of the points within the lake based on the detections. So this is pretty much like a recap of what we saw yesterday, and I just wanted to say that a big thank you to everyone for being here, for being there. It was a great day, great success. So again, thank you. And this is all I'm going to say about yesterday's test. And now it's time to start leading up to today's systems and testing that we will be having here during the day. All right, so day 2 has to do with robust obstacle avoidance. In order to be able to test this type of algorithm, we are relying on a system that we have built. This is the first system that we started working with here in Reno, the Mini-Hawk platform. You've heard it quite a number of times around here in the sessions. The Mini-Hawk platform is a system that was designed to be rapidly prototypable. So this means we can make tons of units of this with 3D printer, and it's a little bit of manual work, but mostly 3D printing is what takes most of the time. And then all the rest of the components in the pipeline, we have pretty much streamlined it. And this is very good because we can leverage that type of platform for different types of applications. This is the very beginning platform that we started out developing in order to do the self-sustainable system design, where you can have solar recharging, takeoff, landing, back-to-back recurrent missions out there in the wild before we moved to deploying that on an amphibious platform. But the most important aspect of it is that it's very cheap and openly available to produce. This has been actually adopted by others who have been using this design as it's available on the GitHub repositories that we have provided for a number of applications regarding the platform. So what's the downside of having a rapidly prototypable 3D printed platform that's supposed to do vertical takeoff and landing and fixed wing transition, like covering a hybrid envelope? It's pretty much it's a flying trick. So it's not the best system in terms of flight endurance, and it serves the purpose of testing various different algorithms, but for a short time span. So we won't be doing like huge missions or anything like that. And this also corresponds to today's demonstrations will have to do with mostly vertical takeoff and landing envelopes, where the flying will be isolated in a smaller zone, and we'll just be demonstrating some of the algorithms that have to do with its guidance with respect to robust obstacle avoidance. Then I just want to mention that this type of platform supports very high level autonomy capabilities, although it's very small, as you're going to see in the field. It carries multiple different sensors, visual inertial sensing, GPS obviously, USB cameras, and on top of everything, it has the same neural processing unit incorporated such that it can deploy algorithms that have to do with segmentation, detection, classification, all those things that you want to do in order to have this basic functionality of learning-enabled execution of algorithms in the field. So what about today's test? By leveraging this platform, we want to be able to test the integration, and this is the most major aspect of the challenges that we have encountered during trying to put this together. The integration of algorithms that are provided by a different group, a different institution that we are collaborating with within the context of the ULI project, and port those algorithms and execute them in the field for real-world testing by leveraging, of course, the environments that are available to us and the field testing sites that are available to us here in Nevada. So what's the fundamental algorithm? It's covariance steering. This is what you're going to be seeing today, covariance steering in order to guarantee trajectories with safety guarantees. And Akash is going to be talking a lot more in detail about that. I just want to focus on the side of the integration testing and what you're going to be observing in terms of the platform itself and what kind of mission profile you'll be seeing today. Before I move into that, I want to say that there is a process for how we deploy systems in integration. Of course, we're never just putting the algorithm on and hoping that it will work. It's a step-by-step process. We have a quite well-tuned simulator that matches the performance of the actual Minihawk robot in the real flight simulator environment. You can see that type of environment up here in some location where it's 3D rendering. We don't really care about that. We just care about the fact that this simulator is very well tuned to match the behavior of the aircraft. This is important because we care to have good match of the dynamics for this particular covariant steering algorithm in order to make sure that what we observe there is also going to happen in the field. And of course, after we've done a sequence of tests, we take it step by step and we take it out to the field, do very piecewise trajectories, very small steps, in order to try to have everything, to make sure that everything works as expected, and observe the data and then take it back into the lab and then back into simulation in order to do more complicated stuff, etc. So this is a great environment here, as you saw. It's, the driving distance out to the field site is very short. So this allows us to do this kind of back-to-back tweaking and then testing again in the real side, which is a very big benefit for us. So yes.
You just mentioned, like when you're doing forensic, post-flight forensic analysis. So have you uncovered things? So.
All sorts.
Oh, that's very good. So I expected there would be an answer that would be positive like that. It's very important, right?
Yes,
But
yes.
Nobody ever talks about how many bugs are found.
Yeah.
This is all configuration managed so that you know what version of software do you write problem reports, or how do you track bug fixes?
This is internally in the lab as far as the Minihawk platform is concerned, and then reporting between teams
What's about the airplane when the bug was covariant steering?
Yes, so this is there's a work group within the ULI project where people communicate about that, and there is a student level coordination of bug fixes for whatever. It's an iterative process, of course, as you can understand. We don't have like high level. We don't have professor level management of individual problems as they are being tackled, but we do have bi-weekly meetings where any problems that are significant and cannot immediately be resolved, or they require a little bit of more communication between team members just to make sure that everybody's on the same side. We discuss those in the bi-weekly meetings where we actually have the professors also attend so that the entire group is aware of how we're addressing issues that we have found. Yeah.
Thank you.
Sorry, just follow up, but you don't have a formal configuration control.
No.
Software.
No. Do you wanted to mention something, Akash? No, okay. I thought you raised your hand. All right. So let's get to today's actual test, because those were just precursor tests just to give you an idea of what the iterative process, the baby steps that you need to do over a long period of time when you're testing those things. Even if it's rapidly prototypable, you can very well understand it takes man hours to build, and we are a small team. We don't want to spend people's time with that, just rebuilding crashed aircraft. This is not what we want to have to do in our spare time. So the playing it safe whenever we're doing tests like that and doing baby steps is our approach. So today's test will have to do with different examples of obstacle avoidance as the aircraft is executing and landing approach maneuver. This is the simulation, not the simulation, the simulated event case of discovering obstacles along the way as the aircraft is coming into land. There's multiple cases, either with two obstacles or a multi-obstacle example. You can see those cases illustrated on the right-hand side, and Akash will guide you through the visualizations and what everything entails. At a very high level, you can, however, understand pretty much what's going on. The red stuff are the obstacles, or blue here on this type of visualization. And the aircraft, as you're going to see, perhaps you can't very clearly see it here, but we will be able to show that in the real field on computers that we will have inside. It has some planned approach maneuver that actually intersects or comes very close to some of the obstacles that are discovered during flight, that appeared as simulated events during flight. And then the requirement is, of course, to have replanned paths that ensure that that there is not going to be any collision with those obstacles, either going around them or ensuring that, based on the uncertainty of the aircraft, we are not going to have an intersection, let's say, of the covariance bubble in high-level terms with the discovered obstacle. So this is an indicative example of a test that tests this entire integrated type of functionality, where the vehicle starts executing a path, and the originally planned path is, perhaps you can very clearly tell it here, it intersects with some of the obstacles, and then the covariance steering algorithm provides the acceleration commands that ensure that the planned trajectory remains within safety bounds as the landing approach maneuver takes place in real time. This is the Minihawk, of course, executing that in the real environment. This corresponds to something very closely equivalent to what we're going to be seeing today out there in the field. As I mentioned, shorter test, nothing like the amphibious platform that have to go through all the loops. Because this type of platform does not also allow for very prolonged endurance flights, but this whole thing is supported at the autonomy level by a small payload that has the computational sensing capabilities that allows this to happen without GPS support necessarily in environments that are going to have GPS noise or that kind of complication arise. Yes.
What's the funnel like cloud behind the aircraft?
I will let Akash explain. You're coming up right after me, right?
Yeah.
I will let Akash explain the technical details. Yeah, I won't steal any of his time. I just want to go over what we expect to see and what kind of system level capabilities the type of system that we are deploying and this type of algorithm on actually has. All right.
So have you been trying to extend your perception software into detecting obstacles?
Yes, we can detect obstacles, but for the sake of simplicity and just ensuring that we're not going to overload the system for these types of tests, we don't want the same stack on the neural processing unit that we have on board to do both learning-based obstacle detection and execute other types of functionalities. We just want an ARM processor. It's not super powerful. So as I mentioned, this is again a very constrained computational platform. So we have very large GPUs on larger aircraft, but this is a very versatile system to do a first level of evaluation for these types of algorithms. So getting to higher level of complications and putting more things together is something that we are definitely considering.
Thank you.
Yes.
When did you start the integration? From get a feel for the timeline.
A feel for the timeline. Gosh, was it a year ago, year and a half ago? Yeah. It's a slow process because you need to establish first the first level of communication, having some weekly, bi-weekly meetings, that kind of thing, but also you need to establish communication channels like what we use together as a team across institutions. Slack is the way to go, and then have some common Git repositories, all the things that you need in order to have a team, which is not something that should be taken for granted. For sure, it takes time, overhead, and everybody's super busy at the same time, as you very well know. So it's always a challenge trying to get people across different groups to collaborate on a common goal. So far, so good. All right, and yeah, really for today, I don't have anything else. Anything else to present? It's all about getting out there in the field and seeing it happen and seeing the actual visualizations take place in real time as the data are being streamed back by the Minihawk platform, and perhaps explaining there on the site and doing multiple back-to-back missions, because we can easily swap out batteries for this type of system that we have there, just in case we want to test if somebody wants to see something else in terms of details. So right. Thank you all again. I will pass it over to Akash for explaining the covariance steering details. Did you have a question? I thought you raised your hand. Sorry. All right. Thanks so much.
Okay. I think Christos kind of explained the higher level demo that we are trying to do. I just want to give a quick overview of the covariance steering algorithm. We have like the longer talk in the afternoon, so I'm going to give more details then. But at the higher level, we have an operator splitting base, which is like an ADMM based covariance steering algorithm, which can handle nonlinear dynamics as well as nonlinear constraints. We have compared it with other standard covariance steering algorithms and found that we can get lower cost trajectories and higher levels of safety and generally greater feasibility. But one of the major issues is that we are doing an iterative process, so that's a bit slower. But in general, like the algorithm can give like real probabilistic guarantees of safety and give like robust controllers that can go around like obstacles and maintain constraints. Okay. Regarding the demo with Minihawk, we are trying to do a terminal landing sequence to a predefined landing spot using our ADMM-based covariance steering algorithm. As Christos mentioned, we'll be simulating a bunch of events and regenerating the trajectories, and also like introducing multiple virtual obstacles. Quickly, I just wanted to cover a few simplifications and assumptions we have to do along this integration path. So the covariance steering algorithm is originally meant to replace like an underlying lower level controller, because what it gives is an open loop control as well as a gain schedule for the period that you are like optimizing for. So ideally, we would like to have like the full nonlinear 12 degrees of freedom dynamics of the Minihawk. But what ended up happening is to do that, we need direct access to the control signals which go into the autopilot. But the autopilot stack that is currently in Minihawk, which is autopilot, doesn't let you access those control signals without getting modified by the autopilot. So you don't have full control to the autopilot, the lower level control signals. So the lowest level we could go with the stack was acceleration control. That basically means that our covariance steering algorithms are going to be like based on like some 3D point mass model. So that introduced a bit of errors in the model, but we were able to like fine tune that and get it out. The other thing is, I think Christos mentioned this too, we have like limited computational power on the Minihawk, and the covariance steering algorithm is like meant to run parallelly. on like larger CPUs. So running alongside vision was like almost not working. Yeah.
So the acceleration interface, this airplane, when you control acceleration on a dynamics non-minimum phase,
Sorry.
non-minimum phase,
Um,
do they have right-hand plane zeros?
no, so this is flying in right now in like VTOL mode, so it's exactly like a quadcopter.
Also, you're controlling accelerations.
Yeah, like inertial, directly giving inertial accelerations in quadcopter mode, so not like in a fixed flight mode. So the acceleration controls are basically like inertial acceleration values that you want to directly control.
So you see, it transitions into forward flight.
No, we are only operating today in VTOL mode.
Oh, sorry.
Sorry if I was not clear about that. So yeah, we are doing the terminal landing sequence. So we are mainly operating in the VTOL mode. So that's what I was trying to say. Like the lower level controller we ideally would like to have is either the direct motor controls or like the thrust and body rate, which lets us give more aggressive and lower level control like to the Mini Hawk. But that's not currently possible with the stack. So that's why we went with the acceleration control. And as we mentioned, like we are doing like completely in VTOL, so the battery life is not that great. That's why we have a maximum of 40 seconds of like good flight time. Because after that, you start to lose the control authority, and this is generally when the last phase, so we didn't want to lose the control authority there. So 40 seconds is the maximum we are going to run today. So we have these visualizations that we will be showing in the field. We have a couple of laptops and we'll be trying to show the live visualizations. So I just want to go over a couple of the key points because this is going to happen really quickly there. So wherever you see the black path, I'm not sure if you can see it. Let me see. Yeah, where we see the black lines, that's the actual path that the Mini Hawk will be taking. That's coming from the odometry of Mini Hawk. So we have several different trajectories. I'll go to the next video, which will be a little bit more clear. Wherever you see this inflated covariances, those are locations where your covariance steering algorithm is recalculating your trajectories, and the covariances are inflated because to calculate covariance, the boundary conditions that you need is where you are currently, so your distribution or your belief. So what that comes from your odometry mean and the covariance. So we have taken like the worst case covariance of Mini Hawk after like running some experimentation, and that's where this inflation comes from. So there is at any point if you're taking an odometry reading, there is that much error in the odometry. So I'm going to just go to the next slide with the video.
So what is it, the covariance?
Yeah, so the covariance, so what we are trying to do is we are trying to make sure that the trajectory that the Mini Hawk is flying is bounded inside the covariance tube.
So this is how well you know your position?
No, this is the how well can you control the system's process noise. So what you're seeing here is how we are controlling the process noise of the system. So we know the system's process noise. Now we are generating controls which can make sure that you can guarantee these safe trajectories. For example, if we say we want a 99% safe trajectory, the controls that we get will work for 99% of the distribution.
This is the covariance of the state?
Yes. Okay. See if I can get that. See if I can get the video running.
In the picture where you know, where those clouds bloom and then it blooms again later, what causes the covariance to
Reinflate.
to get large again?
So that's what I was trying to say. Like when you have to recompute, you need the current state and the current belief. So your current state is going to come from your odometry, and that's going to be associated with some covariance as well. because you have like a
But
distribution.
once you reduce the covariance, why would it get larger?
Because you're recomputing it again. So you're computing, you're computing for 10 seconds.
Is that an iterative?
Yeah, it's an iterative process where you're continuously computing
Common
for.
filters typically don't work that way.
Yes,
Not
but
that you're doing a common filter.
yeah, but we're only taking like the current belief of our position. So like let's say there's a Kalman filter running in the back. It's gonna
I understand. I read what you said there. Okay.
Yeah.
Thank you.
okay, for some reason I can't get the video running. Okay, I'm gonna just show it here. Okay, so okay, so we generally will have a nominal trajectory like this. So we're going to start from this point, and we're going to come around and land. So there is a z-axis drop there. So this is going to be the initial trajectory. So the obstacles are in gray because we have not yet informed the optimizer that there is an obstacle there. So that's going to be an event that comes soon. So as soon as you start executing the trajectory, you're going to let the optimizer know there is an obstacle, and it's going to start recomputing the new trajectories. So that's going to take a couple of seconds, and you get the new recomputed trajectory, and it's going to switch to that trajectory. Now, again, like this obstacle is not yet known to the optimizer. So as soon as you come around, we're going to let the second optimizer be like known to the optimizer, and it's going to recalculate for that. So I'm going to just show that. So now the optimizer knows and started recalculating. And now it has switched to the new trajectory, which is like avoiding the second obstacle as well. Then it's going to come around and try to land. And during the landing phase, we just redo the covariance again so that we get a tight landing towards the end. So this covariance that you see here, the green bound, is generally the bound inside which you should see almost all the trajectories. We designed for 99% safety. 99% of the trajectories should be inside that, but there is a bit of model mismatch because we're using linear. So some of the trajectories might go outside, but that's generally what that covariance represent.
So how did you decide when to tell the optimizer about the obstacle? Is there like a minimum time that you need to keep it around?
So we need around 2 seconds to compute for like 10 seconds trajectory. So for the first obstacle, we just immediately let them know. And so around 2.5 seconds, you get the new trajectory. And when you come around, we just decide an arbitrary time to let them know. So it's not, yeah.
Would there be an issue starting with knowledgeable, but
Yeah, there's no issue with that. You can. There's another demo where we do all 5 together.
Does the red circle represent your covariance associated with how well you know the obstacle?
Currently there is, we are assuming that we perfectly know where the obstacles are. So that's first demo. The second demo, we're going to do something similar, but right now we're going to, for the first, to introduce the first set of obstacles, we're going to introduce 1, 2, and 3 together, and it's going to generate a path. And then just as soon as it starts executing, we're going to introduce the other 2 obstacles. So it has to replan then for like 5 obstacles together. So I'm going to show the video. So we have the first 3 obstacles, and it should have replanned for that now. Now we have introduced all 5, and it's now replanning for all 5. And so these are like the 2 demos that we'll be showing today. So these experiments are like highly repeatable, and because most of those trajectories should be inside that covariance tube. And almost every time when we come for a landing, we reinflate the covariance and recompute so that we get a nice landing trajectory. That's all I have for today. If you have any questions, you can answer.
Does the recompute change based on what we chose as a platform?
Um,
Here, in this specific platform, choose when to do the recomputes because of the platform.
yeah, for the computational time, we have to.
And if you had additional, what would you go recompute?
So there are two things that prevents the recomputation. One is like when you have longer trajectories, if you don't have the correct dynamics, for example, here we have the linear dynamics, so it tends to shrink the covariance and keep it at that point because it thinks because the linear system it can do that. So it is actually beneficial to inflate it so that we can account for any uncertainty that might come along the path. But if we actually have more computational power, we could actually like do this more often. So we can like do it like an MPC fashion and like do it much more often. Yeah.
Is a sphere like a primitive, only primitive with this algorithm works with?
No, like you can have any nonlinear constraints. What happens is like we have a linear, so the subproblem that we are solving inside the ADMM algorithm is convex, so we end up linearizing. So we have like a truss region constraint. We make sure that the hyperplanes are like properly placed. So we can have arbitrary obstacles.
Does the compute increase with the number of obstacles?
Um,
planned for?
It increases very sublinearly because the chance constraint steps are highly parallelizable. Each of them is a projection step, so they can be like compute all of them parallelly.
Is it easy to describe the elements of the state vector that you're propagating there? Position?
It's just
What is?
it's just 3 positions and the velocities. 3D position and 3D velocity.
Is that like inertial?
Inertial, yes.
Question.
Okay.
Out on the spot. What would it take? And how long would it take? You actually have a test for flying.
So we wanted to try in the fixed wing mode, but the autopilot again doesn't have the acceleration control fixed for. So for this specific demo, Pratik, who's a student, he had to modify the autopilot stack to add the functionality for acceleration control. It was partially there, but no one actually developed it. So he had to actually implement those. So if we can implement like those control, like somehow to send those control to autopilot system, we could definitely start trying immediately.
As far as the autopilot stack goes, yes. But what about models that you might need?
I think since we initially wanted to do fixed wing, we have the data from the data that we collected. Yeah, and we have the system parameters and everything already. It's just that we don't have a way to send a control to the autopilot system.
A little bit more development.
Yes.
So it works with non-polynomic constraints.
Yes.
Yeah.
I just want to, sorry, hijack it off for a moment. One of the things that I would think if you have that capability and it's not necessarily computationally intensive is to actually fly Minihawk with the PTIs to do a full system idea across the envelope. And that way you basically create a aerodynamic propulsive model. You have that. And then from there, you can start modifying hardware as you depending on what you're doing. Yes, I suspect whatever else you're doing, and here you have to go to point mass, trimming your systems, but at some point, you may be able to upgrade your computation capability to take advantage of the full model, whatever algorithms you guys are using. And I think having a pretty reasonable six-stall model of fixed off would actually, sorry, fixed off, would actually just for your consideration.
The added value for that would be to establish the process though, because to actually have high fidelities instead of waterfall, that particular platform, it's not the best platform in the world, but if we establish the process to integrate also by steering on board an aircraft, then we can translate that to the other platforms later on. So yes.
So if you guys need any help with actually doing systematically, just pay me because we have a lot of experience with that, especially with those type of.
I'm struggling a little bit with, when, as soon as you tell your algorithm that there's an obstacle, you have to pump up this covariance. A navigation, so is this covariance, inertial coordinates relative to the trajectory that you think you're flying, or what's the covariance with respect to?
It's your current state covariance or your covariance that come from your Kalman filter, like your belief of your state. So
So position and velocities come from a navigator.
yes,
Oh, right?
Yes.
If you're using GPS, there would be no reason why all of a sudden it would explode again just because you told it you had an obstacle.
yes, but that explosion is because we are reinitializing the controller. So the reduction that you see,
So this algorithm doesn't work unless you do that?
no, it will work. But what I'm trying to say is that the reduction that you see in the covariance has nothing to do with the Kalman filter or the odometry or anything. That is making sure that your trajectories that start from this covariance will shrink and come to that smaller distribution. So it has nothing to do with the state covariance. The state covariance only come into the picture for initializing because now you need to tell from where you're starting and what is the uncertainty of your position.
I'll have to read some papers. Yeah.
You have a presentation?
Yeah, I have a presentation with
Yeah, I
that.
know, that's what, we wait for that.
Okay, yeah, any other questions?
There's no other question?
Okay.
All right. Jess, you ready?
Yeah.
Okay. So we're gonna do a few changes just to speed up things since we have plenty of time. So right now, we're gonna have Jessica presenting some of our outreach activities relating to the ULI. Then Professor Mitra, Sayan will give a talk, then we might have a break depending. And Chuchu is online, so I'll keep her spot 1 o'clock. And then we'll push everybody also a little bit faster. Okay.
So you guys go to Tahoe or whatever you want to do. Awesome. All right. Well, thanks. So I'm going to talk about the outreach activities. It's not going to be just for UNR. I'll talk about the other universities as well, what we've been doing. I'll try to answer any of the questions, but I will say I'm not the expert on what some of the other universities have been doing. But it's pretty awesome. You'll also see, so this is something I've always been really passionate about. I think part of it is because the outreach activities that I experienced when I was in middle school is what got me into engineering. And so I think it's important for really engaging the next generation. So you guys might have seen this slide before. Kind of the idea is addressing the pipeline. And this comes all the way from the beginning up through our graduate students. So it's striving to address that STEM pipeline from pre-college through undergraduate and into graduate school, looking at it from a curriculum perspective, our undergraduate students, and then the mentoring, all the different levels down. We want to focus on engaging those students in engineering so they feel capable. I'd also add in here, it's not just engaging them, but also having them see the real world of why they're doing engineering. How can they apply it? What are the problems that they're trying to solve? The undergraduate students, so exposing them to research. We actually had a UNR student that got to go out to UIUC this past summer, and she was able to do research. I know that it has completely changed her career trajectory. It's really been amazing seeing how that inspired her. And then the graduate mentoring. So mentoring the youth and preparing them to lead research projects and individuals involved. So I'm going to start with some of the things that I've been doing. So this is some of the pre-college engagement that we've been doing here at the University of Nevada, Reno. We have some amazing resources around here that we're able to bring through. I'm all about flashy things. So the last 2 years, we've done aviation, the annual Girls in Aviation a Day. It's open to anyone that wants to come. It's put on by Women in Aviation, so that's why it's called Girls in Aviation. We actually have the first ever female test pilot, weapons school graduate from Top Gun that lives here locally in Reno. She's amazing. She's also working on her PhD right now. So between her and myself, and then another Delta pilot who also is a Air Force F-16 pilot, she does both. The three of us have been putting on this event and bringing in the different resources. So we have about 250 local attendees that show up. We bring in aircraft that they're able to see. Fallon brings their aggressor F-16s out. And then you'll see on the right, our Guard C-130s have been there, and then TAC Air, which flies T-38s or F-5s, they bring their aircraft as well. It's not just the airplanes, we have interactive events, so about 30 different demonstrations going on where students can fly simulators, look at rockets that our aerospace club has built, IEEE, ASME, many of the clubs are there as well. So it's really a great event to kind of expose the youth to aviation and the different opportunities. Hopefully this video will play. Yeah, so I wanted to show this. So this is the F-16 taking off, and you can see how excited the students are. Full afterburner takeoff, they're jumping up and down as it goes. So pretty awesome, the resources that our local partners have brought to that event. Let me go back. All right, so the next, I don't know why it's not, okay. Yeah, so the next event that I've been doing, so we had a STEM Discovery Zone that was here this past fall. So up until now, the Reno Air Races was at Stead Airport every year. And so the final year, 2024, they did an air show, and we did a STEM outreach event. And we had 7,500 registrants that came to that event. They bussed in students from all over Northern California, all over Nevada. It was quite an amazing event. You can imagine I was quite exhausted after this weekend. 7,500 kids, is a lot to come through. We had our UNR undergraduate students that were there. And I kind of go back and think about this. Part of the outreach in my mind is not just for the middle school and high school students, but it's also for our college students being able to go out and teach, right? If you teach something, that's how you learn. And so it's been really great seeing our undergrad students and their passion for aerospace. So they were here hosting all the kids coming through and looking at their rockets. And then I hosted an event where I had a simulator, and then I also had a augmented reality. Maybe you guys have seen this video before. I'll go ahead and play it for you. So this is opportune video that I took flying with the Air Force a couple years ago with a 360 video camera. It's me and a T-38 in formation with an F-35. And then we also had a NASA F-18 on the other wing behind a C-17. And so the students can put on the VR headset, be in the cockpit with me, and kind of look around and see what they're doing. So I have a lot of this video. Our hope is in the future, now that we've seen how excited students get about this, creating some more of this 360 video and actually including, there's your NASA F-18 right there, including educational content, because you can do voice overlay, you can inject different things, and so you can make them, you know, really a educational experience. You can flatten the image as well, so you don't have to have it in a VR headset. You can have it on a screen that you can look at, or you can have it in a tablet and you can pan around. So I think it's really a great opportunity to get kids excited and have them kind of experience the flight environment. And then the last event that we've done here at UNR, so we just hosted our Night of the STEM Stars. This was about a month ago. We had 50 different high school students that were honored for their accomplishments. They were able to come. We hosted the event just downtown here in Rio, gave them awards and did some mentorship and kind of inspired them to the next event. And then also our community college students. So we have the Sierra Nevada College here. We have Truckee Meadows Community College. And so with those, we had about 25 college students that are pre-engineering that were able to come and be honored and meet engineers that are in the workforce. With that, so we've also done a lot of the local classes, so the elementary school up to the high school level, going and giving lectures, doing hands-on, building airplanes, flying gliders, little glider airplanes, balsa wood, and collecting data. And that's really a fun event to kind of get them excited about the aerospace program that we're standing up here at UNR. And then the one that I'm really excited about that we're planning on doing this next year. So the Academy of the Arts and Career Technology High School, it's a public high school, opened just a couple of years ago. They're going to start up an aviation academy this fall, and it'll be the first aviation academy that we've had in Northern Nevada. The teacher that's taking it on, I just met with him a couple weeks ago. So he's really excited to work with UNR. They're going to have flight simulators. They're going to have a lot of different things to get students interactive in some of that aerospace education. So lots of opportunities. I said it was my last slide about UNR, but it wasn't. I forgot that I added this. So the other thing for the undergraduate students, so this past year, we coordinated a trip down to Edwards Air Force Base. We took the students and they were able to have a 2-day tour. They were able to see the Vista X-62. So that's the picture that I got all of them next to the Vista. We went over to NASA Armstrong. They got to fly in simulators at NASA Armstrong, see the control rooms, see all the events that were there, get up close to the airplanes. And so I think that also was a very inspiring event for the undergrad students to see the opportunities that are out there. You can see that I like taking pictures, so lots of good pictures and fun things that we were doing. So then at UIUC, a really great event that they've developed over the last couple of years. So they've developed a drone camp at UIUC. So this is where the students help develop by learning engineering in the process. So I think, all these things, and maybe it comes from my alma mater at Cal Poly, the slogan is learn by doing. Well, it's the same here, right? They're building things, they're doing things, they're not just sitting and being lectured to. And so the students and teachers create modules to teach CAD and design of drone airframes. There's a little video that I'm hoping will play. This is from about a month ago. They just did this event. It's not playing. Let me try clicking on it. Now I'm getting in the PIO with my clicker. See if it'll play. Oh. I don't think I'm going to get it to play. All right. Well, if I could get it to play, it's about a minute-long video. And so you'll see these middle school students where they're designing, they're building, they're flying, and they're collecting data on these drones. And this has been an event that they've done multiple times at UIUC. They have a summer camp, and so they've kind of been developing this curriculum and materials for the event. So they develop in the camp, learning engineering in the process. The 3 students create modules that teach them CAD and design drone frames, and then they work together to test, to actually get real data and test these systems. Yeah, so you can kind of see, so here's the little drone areas with the faster speed. You can see them flying it and collecting the data on it. And then the summer, so they do summer camps that are more extended. You can see Naira here with the students, and this is where they have middle school for girls and for other groups to come in and learn these processes and apply them. So, and I think Naira, she just walked out. So I think they've already done this one time for a summer camp. They're continuing to develop it. So the plan is for this to be a continuing event. The camp will look like to build that functioning drone. They identify the needs and constraints, so learning kind of an engineering mindset. They create the plan of creating that CAD, making 3D printing the frames, so doing the hands-on printing of it, testing it to evaluate their design, and then improving the redesign of their drone, an iterative process. And coming from flight tests, I love seeing that they're doing this because I think there's a lot of value in actual hands-on data collection and analysis. They work in a group, so working together, communication and teamwork is really important. And then each group's design is going to be a little bit different, so they can learn from each other, see the mistakes, and see how the process works. This really, engineering very rarely is it a single person sport, right? It's a team sport, so it's important to learn those early on. Having middle school students do that is really important. And then for the North Carolina school, so there's the events that they've been doing, really focusing on the third grade to 8th grade students. And they're using it at the Next Generation Academy, and they've been focused on robotics. So a robotics event where they're looking at basic programming and then education that goes along with that, using basic hardware automation. They have a STEM robotics, and I know a lot of schools are doing this, STEM robotics outreach, really looking at some of the minorities that are in that area, 3rd and 5th grade students. And then the emphasis is on programming and automation. They manage the outreach event to high school students and adults, focusing on the robotics for hardware and software development. This is the recent call that went out. So you can see that they did this specifically out of middle school. 33 students were involved. It was a 6-week long process. Once a week, they were doing that, and you can kind of see the demographics of the students that were involved in the do-it-yourself drone project. And then finally, is talking about our undergrad students. So we've had 3 students now that have gone through the RU program, 2 of them from UIUC, and then the most recent one, Caitlin, who came from University of Nevada, Reno. So Caitlin had actually been at UC Davis working on an aerospace engineering degree. The out-of-state tuition cost, and then also having family, she decided to come back to Reno. So she had been here for about a year, really wanting to get into aerospace. So when she heard about this opportunity with UIUC, it was amazing for her. So she spent the summer there, where she had mentorship from postdoc students and from professors. And then she was able to learn and do research. She's brought that back. And actually this summer, she'll be doing a research program with Panasonic Energy here in Reno. And I really think this opportunity has given her, made her resume look good and really, kind of built her and her confidence in her career. And then highlights, so the undergraduate education, so they were able to present at professional conferences. So being able to get up and present their results and work on their public speaking. They participated in professional development opportunities, and then they were mentored by different, and they went out and mentored different pre-college students. This is an ongoing program that UIUC is going to be doing. So they're actually recruiting right now to figure out their next cohort that will come in to do this research opportunity. And then finally, our graduate, so the graduate mentoring and leadership development. So this is where we have mentoring for our undergraduate and college students, working with the research students that come in, using pre-college curriculum assistance. So again, this is kind of where I say you learn by being the teacher. So I think with our graduate students going and mentoring and teaching the next generation, it helps them learn as well, develops them. And then it provides, that formal feedback to the graduate students. So that pretty quick going through all of it. But the overall goal, as I mentioned, is addressing the pipeline from, the earliest ages, 3rd grade up, all the way through our graduate students and focusing on those STEM opportunities and engagement. So with that, what questions do you guys have for me?
That's impressive.
Oh yeah. I'm super passionate about outreach. It's important. I'd also say, I thought about putting some numbers in here. Other countries are starting to surpass us, right, in the number of STEM graduates that we have. And so I think it's very important to get students excited. And I think just showing the technology is not enough, showing the why, how does it matter? So that's why I'm always out like, all right, let's show why you're doing this. How does it matter? That'll get kids excited. So, yeah. You're right.
It looks like a unique person, but you haven't done it. Oh,
How many people?
I think it's slow myself, really. Well, so I mean, but that's one of the reasons that I'm really involved in our UNR. So like we call it train the trainer in the Air Force is what you say, you train the next person. So that's my UNR Aerospace Club students. I bring them along, right? And so all these events that you'll see that I've done, I'm always trying to bring along UNR students. I actually have one. There's one, it's Carson, so he's in some of the previous pictures, and he's the first, maybe the second person I met at UNR. I hadn't even started yet. He gave me a tour of their rocketry, that they're doing. And I asked him a million hard questions. I didn't mean to. I'm like Evan, and just asked hard questions, and he answered all of them, and I was so impressed with him. So actually this summer, I got him an internship with Electra Aero. You guys have heard of Electra, they're out on the East Coast. I have a buddy that works there, and Carson's awesome. I want you to bring him. So they bring him, he's gonna be an intern. And so I told him, I was like, hey, while you're there, I want you guys, well, I don't have any influence over, but it would be really awesome if you guys document what you're doing, do some papers, bring it back to the university, because they're going to be doing flight tests, bring it back to the university to inspire the next generation. So there's only one of me, but I'm trying to build more people that have the mindset.
And you really the energy and the enthusiasm.
That's
why you've done. It's amazing.
Well, it gives me energy, to be totally honest, right? Like you surround yourself.
Yeah.
You surround yourself with kids, and they, they'll think, oh, that's fun. Oh, you're right. That is awesome. Yeah, it reminds me.
Just had 2 comments. One is, other than this is really awesome, please encourage people to look at mass. Internships, especially in the summer, because we have, I mean, hands-on and it's a great way, even if they have no intention of working for NASA.
Yeah.
But coming in and just seeing that, besides it helps their resume now. That was, the other one is, I think this idea of not only showing them the technology, but having them work on stuff, I think is incredibly important because too many people get discouraged. They hear it's too hard, it's X, it's Y. Having them do it in a fun environment where they've succeeded may inoculate them from those who say, well, why would you want to be an engineer when you can, make an easier path to do something else?
Yeah, well, and I think, this is one of the challenges of instructing too. You want to allow some failures too, right? So it's like trying to find that environment, that balance, right? You want to, I mean, it's, if you succeed the first time, it's actually less rewarding. But if you have a couple struggles and a couple failures when you work through it. And so that's what I love, with the UIUC drone program that they're doing. I'm sure they don't show the failure videos, so I'm sure there's been failures, right? I'm sure there's all kinds of struggles that they're having with it. And it makes it, makes it more rewarding. So I'm excited. I mean, we'll see, what you guys have been building here at UNR. I look at that little case talk and look at some of the things that we have here. I'm like, these are somewhat disposable things, right? We can use these for the same type of learning opportunity.
So just a thought, sorry, undergrads, right, work for work.
Yeah.
Make them build.
And they love mentoring. Like I have a 13-year-old daughter, and whenever I bring her around, all the college kids are, like, oh, what do you do? They want to show off what they're doing and they want to mentor. They want to mentor the next generation. So that's kind of you build the ladder, right? You build it up.
Yeah, I was thinking for a new curriculum. It's like we had something that's called, essentially was a figure thesis that was just done during the year. But it's like a project. It's a semester-long project, and you start the whole process that doesn't get credit, which you get an opportunity to get your hands and do real things. And so you guys want to build up capability. I mean, perfect. Make that as part of your.
We got a counselor beside.
I mean, I'd imagine at some point we design build fly, right? You look at other schools and they design
That's a
fly.
huge-
Huge.
The additions.
Yeah, so I'm, I know we're a couple of years out from that, but I'm looking at that's such a great opportunity. And again, they're gonna learn the most, the ones that crash their airplanes. They're the ones that are gonna learn the most, right? So,
And if you did, then push them to the next part of thing, right? It's like he says, spiral. Okay, you got this thing, but now here's what you need to add to make it a little bit more real. Oh,
Yeah.
Eventually you'll fail, but you'll understand and not.
no, it's exciting. I mean, and that AACT school, so the principal there is higher energy than I am, and more passionate about this than I am. So it's amazing, just the partners, and there's just a lot of energy in Reno right now, because there's all this stuff that's standing up, so it's lots of opportunity. We'll see. What other questions? Yeah.
On the deal.
Yeah. Well, awesome.
That's Jessica.
We need to ask Jessica to all the facilities.
For sure.
It's really good to see that something came out of this, usually on this, not that I'm always negative, but a lot of lip service gets paid in this on programs, but this is.
Well, I mean, you have the right team, and I'm sorry they can't be here, but Stephanie and Joe that are both at UIUC, I mean, they put so much work into this. I mean, they're amazing, and I think they really value that. Again, developing that drone camp program, right? Like developing hands-on opportunity.
Yeah.
So
I may ask you to give this talk as.
yeah, I love talking about outreach. Passion. Anything else? Okay, I'm done.
I think. Go with Sayan. And yeah. EC2 type of work.
Hard act to follow there, guys.
Yes, I know. I was just going to say that, Jessica Peterson is hard to follow. Not typically.
join the teams and share the screen. Let's do that.
Okay, so I have to do this thing of swapping the thing now. There is the cursor. All right. Okay. Okay. So this is going to be the talk that goes with the demo that some of you saw yesterday. Younger and John. Let's see, John. Yeah. Younger and John did the demo yesterday. It's going to showcase this verse tool and what we are able to do with the tool now. Several other people have contributed to this work, Alex Wan and Daniel Zhuang. Okay, so I want to spend a few minutes setting this up and sort of talking about the background and motivation for why we are doing this, and then I'm going to hand it off to Younger, and he's going to do a brief version of the demo. And if you're interested to get a live interactive demo, it's still set up there, so you can set up different scenarios and look at it in more detail. Okay, so we are changing gears here a little bit. Last few days, the discussion was about autonomy on individual vehicles. So we are now going to talk about the airspace. And this is also a very important piece of the puzzle that will ultimately help us have flying cars and air taxis. This is a projection from a paper which shows the number of deconflictions per square kilometers per hour is going to be of the order of 3,000 plus. And you don't have to believe me for this. Parimal Kupardekar, NASA director, has also said that ultimately the airspace logic is going to become the constraint for having this technology available to people. So if you have like 3,000 deconflictions, you're not going to be simulating only to assure safety of these protocols, right? The old saying from Dijkstra, simulations can help find bugs, but simulations and tests can never show you absence of bugs in a protocol like this, right? So that's why we want to go towards mathematical models and verification. And that's what this particular tool Verse is about. We are creating this framework which will allow us to actually mathematically prove correctness of deconfliction protocols. So today we are going to talk about one particular protocol, but Verse is designed to be a much more general tool for different kinds of protocols, different kinds of vehicles. Just to remind you what the verification problem is, so this is a picture that many of you have seen before. So the input to a verification engine is some sort of a model of the system, which could be a model of the vehicles in differential equation form, the logic for collision avoidance that could be code. In this example, it's going to be a neural network for reasons that we will get into in a moment. So that's the input to the system. And then the verification engine does analysis on this described scenario or the model. In this case, the analysis is going to be fully automatic. And then the output of that is either a proof that indeed the protocol is safe in the scenario in which we are verifying it, or it is a counterexample illustrating that here is a particular situation, a setting in which things can go wrong. Okay. And usually when we think about verification, we focus on this certification part of it, like it gives you a proof. Okay. And that's indeed one of the major outcomes of this process. These proofs ultimately will help us gain the public's trust on this system. Maybe it will convince organizations like FAA or NHTSA that indeed the protocol is safe, and there's reason to believe that it's trustworthy. But the other outcome from this formal analysis is also important to keep in mind. It helps us discover the boundary conditions, the operating design domain, so to speak. What are the ranges of velocities? What are the visibility ranges within which we can deploy these vehicles and the protocols? Often in a proof, right, in a theorem, the assumptions under which the theorem holds are equally interesting and important. It helps us discover the correct definitions of the concepts in which the theorem holds, right? So in applications of formal verification also, I find often discovering the boundary conditions is an equally important outcome of this process than just the final proof. Okay, so that's one point I wanted to make. Now I want to take a moment to step back a little bit. I've been working on formal verification for more than a decade at this point. So I think of this whole pursuit as a part of a bigger quest, if you will, and many of us are in this business. So we are trying to ultimately use math to solve some useful problems, right? That's broadly what formal verification, control theory, all of this is about. But if you want to build tools and techniques that are useful, you have to think about the cost of using these techniques as well. And then there are these benefits. So in a way, we are all chasing this mythical green land of where tools can be useful. So let me talk about this for a second. And this is inspired by this recent blog post by Mike Dodds. He's at Galois, works on formal methods. But this kind of a picture has been in my mind for a long time. So I want to sort of spend a moment talking about it. So, there are a couple of extremes that you would immediately recognize. So simulations, very low cost, right? Everyone does simulation. Undergraduate students are writing simulators to evaluate, and test their protocols. And there are limited benefits. You can find some bugs, as we said earlier, but it's sort of limited in how much assurance you can get from some simulation. And then the other extreme, the top right corner, are these theorem provers, POC and Lean. So typically, if you're using a theorem prover, you have a PhD. But it's also a very general purpose tool, and you can prove statements quite rigorously, and they're very expressive, right? But high level of effort and cost is needed to be able to use these theorem provers. So, for example, people are using theorem provers to prove correctness of nuclear power plant safety mechanisms, or security of AWS protocols. So somewhere in between, we have things like falsification, TLA, where our research started. So when I was in grad school, there was this tool called HiTech. I don't know if any of you know about this. This is Tom Hensinger's work. Beautiful original theory in hybrid system verification, and they built a tool. And actually, the tool was quite well engineered for its time. Even now, you can download and run it. But fair to say, no one outside of academia uses it. Okay? Because you have to learn this specialized language to use the tool. And along that line, there are tools which makes the tool much more usable, handles nonlinear dynamics like Flowstar, but still sort of difficult to use. You better be like a grad student in a particular group to be able to use that tool. And so our journey in that has been to try and make these tools more and more usable. So C2E2 was a tool that we built in 2013. And at that time, it was about MATLAB. So Melchior was talking about MATLAB yesterday. So we wanted to make this tool connected to MATLAB and Simulink with the hope that, this will make it more attractive to engineers, because directly from MATLAB models, you could do this kind of formal verification. For reasons I won't get into, didn't really work out that way. We had UI and etc. So it was nice paper, but no one used it. Then there was the dry VR work. Here, the main intuition was, you don't actually want to have to write down every part of the model, because often you're dealing with systems where certain components are too difficult to write down a model of. And so you should be able to use statistics for the black box parts of the model, but not sacrifice rigorous reasoning for the parts of the system where you do have a white box model, like you have differential equations or logical formulas, right? So how do you bring in black box statistical reasoning together with white box formal reasoning under the same umbrella? So that was the intuition behind dry VR. This was, by the way, Chu Chu Fan's PhD work, well recognized, ACM dissertation award, and so forth. So it was getting closer to, I think, this mythical land of usable things. But again, I don't think too many people are using dry VR. So with this verse work, our hope is we are shooting for something right at the heart of this usable formal verification tools. And our North Star here is the success stories with CBMC. So CBMC is the bounded model checker for C++, and it has taken the world of formal verification by storm in the last few years, primarily driven by Amazon. So Amazon has been using CBMC for their production code, and then there are also similar things happening inside, Facebook and Google, and these are the papers that are coming out of that work. And the one takeaway that is the analysis has to be fast, and the tool has to be integrated inside the designers or the developers' IDE, right? So you're writing code, and inside the same environment, you're running formal verification, rather than going to a different tool flow and then verification in a different environment altogether. No one wants to do that, okay? Developer time is very valuable. So that's our main motivation for developing Verse. So everything is Python. You could potentially write code and call Verse to verify the code inside the same framework. Okay, so I just wanted to give that as the background.
Can you just comment on
Yeah.
something that you somewhat touched there? We want the V and V isolated from the developer. We don't.
I see where you're coming from. Yes, so maybe the idea of exactly how V&V has been successful in software does not apply to aerospace, because you explicitly want this to be separate enterprises, separate sort of endeavors, right? So maybe, yeah, so for someone like Boeing developing commercial, you want this separation, but maybe, I don't know, if I get Boeing to use my tool, that'll be awesome, we'll figure out. But right now, maybe a more achievable nearer term goal is to get robotics companies, smaller companies, to incorporate these tools in their development pipeline. Right? Okay, so what is Verse? It's a Python library for modeling and verifying multi-agent scenarios. You will see that the agent decision logics can be very complicated, thousands of lines of if then else code, but it's all in Python. The scenarios are described by instantiating copies of these agents and describing how they interact with each other using sensors. Again, it's all Python. You just instantiate certain objects and classes to define a scenario, and then you say verify. Specifications, again, no need to learn some new fancy temporal logic. You write asserts in Python, and that's it. And again, I'm saying Python not because Python is the most amazing language, just because it's more popular. If you buy into this idea, then a similar thing can be done for any language. C++ it requires effort, but I don't think it's like a major intellectual leap. Internally, Verse does reachability analysis. So it does take this idea from DriveVR, which is for the parts of the model which are white box, like the code and the differential equations, we will do model-based analysis. But then if you want to incorporate a piece which is too complicated, we will use statistics to get bounds on those parts. And are we really in that orange zone? I don't know. But I can tell you that currently Verse is being used by 90+ students every semester at Illinois in a course on autonomy. They design a simple automatic emergency braking system, and then they check it with Verse every semester. Okay. There are some complaints, but we are doing a user study which is going to appear in this computer science education conference. It seems like it is usable, and students are finding some value in discovering bugs in their logic early. Okay. All right, so now let me tell you about the case study. So I'll just do a little bit of setup, and then Younger is going to take over. So we are trying to analyze scenarios with multi-agent collision avoidance with realistic aircraft dynamics. So the collision avoidance logic is going to be this protocol ACAS-XU, which was developed earlier on in MIT Lincoln Labs. So basically the way the protocol works is you have an own ship, which has a certain heading and some velocity, and there is an intruder ship with its own velocity and heading. And the input to the protocol are a set of 5 variables: the distance between the two vehicles, their relative angles, their speeds, and the headings. And then the output from the protocol is what are called advisories. So there can be 5 kinds of advisories. Clear of conflict means you don't have to change anything. Weak left means take a gentle left turn, and so on and so forth. But the original ACAS-XU protocol was actually developed from observing pilots, and it was a huge table. The size is about 180 gigabytes. And then it became sort of impractical to deploy this protocol on smaller UAVs. So what some other people did was to sort of distill this table into a compressed form, and that is what is represented as a neural network. And it became, 3 orders of magnitude smaller, 120 megabytes. So this ACAS-XU neural network is the object that we are studying. And it has, by the way, become a pretty important benchmark for neural network related verification problem. There are like hundreds of papers using this as a benchmark. Where we are different from the other papers is that we are closing the loop with the aircraft dynamics. And not only that, our aircraft dynamics is by far much more realistic and complicated than anything others have done before. Okay, so what is this? Yes.
Okay. Wait, so these output strategies there, I would think would be very dependent upon rho.
Yes.
So if rho is large, often a small speed adjustment in one of the vehicles deconflicts.
Yes.
Then you're not changing trajectories. Then as rho gets smaller, then say in mid-range, some weak left, weak right, then as rho gets very, very small. So do you have that?
It's all in the protocol. So we did not change the ACAS-XU protocol at all. So maybe John, you can comment more on this because you have insights on how the protocol actually works. The protocol came about from studying how civil aviation pilots actually do deconfliction. And that was in the table. And then from the table, people sort of compressed it down to a neural network. Right? So whatever is there is what we are dealing with. We didn't design or tweak the protocol in any way. Yeah. And since you are, I remember one of your comments from an earlier meeting, which I wanted to address. So basically, one of the approaches we were taking to do this whole closed loop verification was to simplify the neural network itself with a decision tree, because that would fit better with our verse way of doing the analysis. And you asked a very valid question that how do you know there is no gap between the neural network and the decision tree? So we didn't find a very good answer to that. We are still continuing to pursue that, but today we are going to not do that. We are going to just directly verify the neural network. Okay. Yeah.
ACAS-XU two-dimensional, so two-dimensional velocities and dimensional.
The velocity is just one dimensional. It's a speed, right? And there is separately a heading angle which tells you what is the direction.
Still two-dimensional.
Pardon?
Still a two-dimensional representation.
So the airplanes are in 3D. So the airplanes are in 3D. The input to the protocol are these 5 variables. There is the scalar distance, there are the relative angles, and the heading angles, I think, capture sort of three-dimensional angles. John, did you want to?
Yes, so those are 2-dimensional, but the 3-dimensionals kind of handle those vertical partitions kind of on the neural networks that you choose there. But these state variables are kind of 2-dimensional representations, and then the vertical information comes from which of those 45 neural networks you choose.
Yeah, I didn't talk about that. So let me expand on that. No, thank you. So basically, there are 45 neural networks actually, not just one. And so the z-axis has been split into 9 zones. And depending on which zone the airplanes are in, you are invoking the corresponding neural network.
Okay, so that's what we
Yeah.
and vertical partitions.
Yes. Thanks. Other questions?
I think that's our first question.
The waterline
the particular outcome of the advice from the unit, not verifying the unit was correct. Like I extent from you, you can verify my answer is correct, no, but you're not verifying the claim. Right?
No, let me hold on to that for a moment, Louis. I'll tell you exactly what we are going to verify. The short version of it is we are going after verifying all possible allowed scenarios in which two aircraft, or actually more than two aircraft, are going to interact using this protocol. So it's not just a one query to the neural network. It's going to be sequences of queries because the airplanes are flying and constantly running the neural network. But also we have to cover the entire space, right? So we are going to talk about sets of possible states that the aircraft are in, and what are the corresponding advisories that are going to come out of the neural network, corresponding sets of advisories. Yeah.
Solution for
Correct. Output of the neural network.
not the neural center. Like you can go on the claim, like I take something, say,
Well,
you're doing this on like on what you can work like that, even a half. Say that you can work like that one. An essay or a solution.
so to verify the output of the neural network, we have to actually evaluate how uncertainty flows through the neural network, right? So there is uncertainty in these 5 variables, right? That becomes the input to the neural network. The neural network has all these layers and branching and all that, right? So you have to flow that uncertainty through the neural network to say, what is the set of advisories that can come out? And for all of those, we have to assure that the system is safe.
Because I would say that for something stochastically same, right?
But that is done, right? This is not training the neural network. This is a fixed neural network.
It may not converge deterministic every time.
But that is not my problem. The neural network has been trained already. I am dealing with a fixed artifact, which is a deterministic function.
So where you encounter a outage or you will fail, or you say you won't fail.
So the notion of so the notion of distribution does not arise here, because what the claim for ACAS-XU, if it is correct, is here is the range of distances and angles in which the two aircrafts are interacting with each other. Is the protocol safely deconflicting them or not, right? So there's a range of possible values of those 5 variables. And if I am able to cover those ranges, I'm good.
I have doubts. Said, you know, written by Python. He conveys the bound we use. Some all the back, you say back software will be correct. There are numerous bugs in Python. And they are, is that primary protocol or the cloud you can run this. Is that true?
Sorry, I didn't completely follow. So the concern is like the Python itself is introducing some bugs. Okay. So
if you look at the work,
okay.
that means the bugs doesn't matter.
No. Okay. So if I understand your question correctly, it's a important question. Let me address it. So all of these claims about verification that I'm making, not just in the neural network, it's in verse, in the reachability analysis, all of that, right? So I would say this is modulo Python is correct. Python's numerical engines are correct, okay?
Sure.
You have to start somewhere. Yeah, you have to start somewhere. So that's where we are. If, for example, Boeing believes that this is the way to do it, we should build a qualified tool where we are sort of,
yeah. 100% that.
Yeah.
Unfortunately, the assumption is very old. But I think it's much more rigorous to say that verify the solution of this part. You will get this correct. Otherwise, you're equivalent to say that you can verify doing this correctness without knowing this internal. If one line aligns that you fit, not you. When I said, I did not particular day, I will onboard all this.
Let me, yeah.
So then you can look at all the cases, but you cannot prove that. So I didn't written the bias by particular day. I would just output focus. You cannot prove the accident. Which is like, oh, not malicious, like just some kind of array of a number.
Let me get a little bit more into it and,
That's not a server.
pardon me?
Question. Essentially, it boils down to a fundamental question. If we don't have observability, that means when the bug in the software, they're not getting triggered by particular computation state and data. So when we don't have, basically, there's a fundamental thing, is that for things not observable and measurable.
Okay, so you're saying all these things about observability, measurability. If let's look at the actual system that we are verifying. I would like to understand what. Okay. Okay.
Just say, I saw some very hard problems. You can verify I did it right or not, but you cannot verify which I never made a mistake. And I don't believe I'm doing a mistake either.
Oh, I don't understand what the concern is. Yeah.
You have a piece of software, you don't have that. The state space is very large.
State space is 5-dimensional here. The input space is 5-dimensional here. Yeah.
There are certain state space may not be triggered during you manage business.
But that is where reachability analysis comes in, right?
Yeah. On the transaction, not the reachability inside the neural state.
We will compute the actual states that are reached inside the neural network. Yes. Yes. Yeah. Yeah. No, like I said, to propagate the uncertainty in the input to compute the actual set of output, you have to propagate the uncertainty through the internals of the neural network. That's precisely what we are going to do.
Okay.
Any other questions? Okay, so quick word about the dynamics. The dynamics here is also complicated and interesting, and this is where there's a lot of integration with NASA as well as the other aspects of this project. So we are working with this Guam model. It's this 25-dimensional aircraft model we got at the beginning of this project. In particular, we are working with this JAX implementation of the Guam model, which was done by colleagues at MIT, Chu Fan's group. So that's what we are building off of. And yeah, so many of you are familiar with this model, so we don't have to explain this further. So here is the actual problem that we are solving. It might help understand, clarify some of these questions that came up. So each agent, so by agent, I mean a combination of the dynamics, the airplane, and its decision logic, right? So each agent has its own decision logic, the neural network, and the 25-dimensional vehicle model. And we'll have instances of several such agents, right? So we'll go up to 4 today, but it's potentially can be scaled up to even larger number of agents. ACAS-XU is actually just designed for pairwise deconfliction. And then a scenario is defined by also describing how the agents see each other, okay? So, so we need a notion of a sensor model. And we can, in fact, introduce noise in the sensor model, right? But to begin with, the sensor model could be very simple. You get to observe the ground truth relative distances between the 2 airplanes and the ground truth relative angles between the 2 airplanes, right? So that sensor model then produces the inputs that go into the Guam decision logic, which produces the advisories. So that's the whole closed loop system, multiple agent seeing each other through this sensor model. And yes.
Could you just comment on, this is running continuously or at 100 hertz or
Great.
Is there an event trigger or?
Yes, great question. So it's every 0.1 second?
Yeah, 10 hertz.
10 hertz. It's running at 10 hertz. So every 10 hertz, you make an observation of your neighbor or all the airplanes. That input goes into ACAS-XU, you get advisory, you follow that advisory for the next 10 milliseconds. The safety property that we care about here is near a mid-air collision, which is defined by 100 feet of separation in the vertical direction and 500 feet in all of the horizontal directions. So that becomes a Python assert, basically. And yes, so I think we have already talked about this, although the whole system is deterministic. If you fix an initial condition, and you have no sensor noise, then there is a single execution of the whole system. But for verification purposes, because we want to cover the entire envelope of the system, we will have uncertainty in the initial conditions of the agents. And that uncertainty is what has to propagate through this closed loop system. Question.
So currently you have multiple networks for every particular connection, right? What happens if you get a conflicting advisor?
We'll consider both of them.
Okay.
So yeah, so you have a set of states. The state space is this row of this V, right? So that set of states will go through the neural network, and it can produce multiple advices.
Yeah, for example, let's say you got both peak left and stop.
Yeah, we'll do both.
So how do you go about deciding that, like, which is the, which can?
We will non-deterministically do both, right? So think of an automaton. You don't know the current state of the automaton exactly because there's uncertainty. So we'll have to follow both branches. So it's conservative, but if you have proven safety this way, then you're guaranteed to be safe. Yeah, so that's what we want to do, right? So we want to propagate uncertainty, ideally cover the entire space of interactions, and if it proves safe, then we are done. And this is where I hand off to Younger, I think.
Yeah. So before diving into exactly how we do it, I want to quickly show some results first. So we create this nice looking GUI for this scenario. And what we can do is, in this scenario, we instantiate two aircrafts. You can see there's two small aircrafts on the top, and we specify the initial condition for each of the aircrafts. And both of them is running like the ACAS logic. So the first thing that we can do is we can run simulation of the scenario by pressing the simulate button. And here's what the results looks like. So you can see we have this blue airplane starting at the bottom and going upwards, and the red airplane starting from the top and going down. I mean, on the PowerPoint is like going downwards. And we can also see both planes perform like a strong right maneuver and to avoid each other, to like avoid collision. And this behavior actually match like the common practice in civilian aircrafts, like the pilots would turn right to avoid collision. And we can, just besides simulation, what we can also do is reachability analysis. We can do that by pressing this verify button, and here's what the result looks like. So instead of computing like individual trajectories, now we can compute these reach tubes as shown in the plots. And these reach tubes actually enclose all the possible execution of the system starting from the initial condition that we defined. Okay.
Could you repeat that? What kind of tube is this?
Yeah.
I didn't understand the word.
So this is a reach ball, a reach tube. And
Very good.
okay.
Thank you.
So how can we do that? So this multi-agent ACAS XU plus Guam system can be modeled as like an iterative interaction between Guam and ACAS. Like we are starting from a single initial state, and we can propagate that initial state through the Guam dynamics, which give us this 25-dimensional Guam state. And then this Guam state will go into the sensor, which computes like the ACAS inputs, like the 5D ACAS inputs. It will then go into the neural network, which computes us like one of the 5 turn advisories. But the thing is not that simple. So we have uncertainty here. Like first, we have uncertainty from the initial condition, and we can see if we have that, then all of the states in this kind of block diagram will go from like a single state to a set of states. In addition, if we consider about noise from the sensor, it will basically further bloat like this set of ACAS states. So how do we handle that? So first, we are analyzing like the ground dynamics and the sensor noise using our hybrid system verification tool VERSE. like we can compute the reachable sets for the continuous parts of the system. And what about the neural network? So for the neural network, we utilize a neural network verification tool called Alpha Beta Ground. It's one of the state-of-the-art neural network verification tool. And what can it do is it can, given like a set of inputs, it can actually propagate this set of inputs layer by layer through the neural network. And it can give us like the set of outputs. And this basically, and if we have this set of turning advisories, we can then close the loop. So
That will give you coverage of the network. So how do you know you're touching all the neurons? How do you know you're touching all the paths through there?
this is
Yeah, so maybe I can take this.
Yeah.
So yes, so it is computing an over approximation of every layer that is being touched by the current set of inputs. And by doing it layer by layer, you get the over approximation of the output. And in a nutshell, I mean, this is a big community now of people who are developing neural network verification tools. Crown is the one because Juan Zhang, the developer, is at Illinois, right next door. So easy to collaborate with. But there are others. So we could plug in a different tool if that suddenly became more powerful for some reason. And the way it works is basically it's trying to create piecewise linear over approximations of all the internal variables in a layer by layer fashion.
Yeah. So let me show some more results. So again, this is a two aircraft scenario, similar to what I've shown earlier. The major difference is now the two aircrafts are more head up. And again, we will first show the simulation results. And what we can see from the plot is, in this case, in all the simulation results, like the blue airplane is doing like a slight left turn to avoid like the red airplane. And now let's perform the reachability analysis, like to compute the reachable sets. And what we can see is actually there's a branching happening. Like it's already showing there, like in some of the cases, the blue airplane will not just turn left, it can also turn right. And this is actually a rare occurrence in this scenario. Like we do many simulations and we confirm that this is a rare occurrence. And this is showing that the reachability analysis can easily capture this kind of rare occurrence in the scenario, while the simulation may miss it. So for the last demo, I want to show here is like a scenario with 4 aircrafts, and 3 of them is running the ACAS logic, and 1 is just doing like it's just going straight. And what we can see is the tool that this pipeline that we developed is able to properly handle this kind of like scenario at the scale. Like we can do simulation for it. We can also compute reachability and compute like a reachable set for this scenario, but it will take like longer time. And I'm not going to show it here. Okay, so that's the end of the demo. I guess I will hand it back to Sayan.
Any questions on the, yeah.
Go to slide, right?
This one?
Yeah, so you have 2 blue branches.
Yes.
Can you explain why they haven't been merged?
Yes.
One big branch?
Yes, so the reason is this. Let me actually go back to this slide. So you can see now with all this uncertainty that we introduced in the initial states and the sensor, we will have the inputs to the neural network will be a set. There will be a continuous set of inputs to the neural network. In this case, you can imagine the output from the neural network can potentially also be a set. And in this case, there can be multiple valid advisories that can potentially happen at the same time. And that's where that branching is coming from. We are exploring all these possible advisories that can happen in this scenario.
You internally, disentangle these two.
Yes, yes.
What was the order of like verification time? That takes, because I've used Alphagram before, just like try to continuously send requests. It's kind of been a slow right now. Phase 5. So what's like the order?
So that's a good question. So first is Crown is actually not a big deal here because we are running it at like 10 hertz. So it's like for when we propagate the dynamics for every 100 milliseconds, we invoke Crown. And I think their implementation is pretty good these days and it runs pretty fast. But there's still a problem here because you can see we are doing this branching. So in the worst case, you can imagine there will be an exponentially amount of branches. We haven't tackled this yet, but I think this is an important next step. Like we will have to either merge some of the branches into like one branch to reduce this order of magnitude, or we have to explore some of the symmetry property of the system and do some caching to reduce the amount of computation needed. I think that's the immediate future work.
Still, can you give some order of magnitude kind of numbers as to how much time it takes with 2 aircrafts, maybe 4 aircrafts?
So
Might even have a
it's
table
kind of
for that.
depending on the scenario. So for this first scenario, like we have less branching. We all ignore simulation because it's always pretty fast. So this one will take about 2 to 3 minutes to finish for the verification. And for this more complicated, like this more complicated one with much more branching, this will take much longer time. It may take about 20 to 30 minutes. For the 4 aircrafts, I think it will not really be a feasible time.
And this is all running on a laptop, and we haven't really looked at this problem that Younger is saying to exploit GPUs or parallelism or symmetries. So if you really wanted to cover the whole space of approaching airplanes, you could potentially run it for a few days on a big computer and still get the coverage that you need.
The sensor noise and things like that.
Okay, that's a good question. So the way that we are putting in the sensor noise is you see here, we load like the set of ACAS inputs. So we model the sensor noise as like a constant amount. And we have some more results about this sensor noise. If you are interested, just come to me after this. Yeah.
So your sensors are estimating the velocities of all agents on every ship independently, with no communication between any of the agents?
We are doing pairs of agents. And currently for the multi-agent setting, like the number of agents greater than 2, the setting that we are doing is we are only looking at the nearest agents.
Yeah, so ACAS-X is designed for a pairwise thing. So when we show these results about multiple airplanes, we are making some choices here, which maybe the original designers of ACAS-XU did not intend us to make. So we are, I think, choosing the nearest airplane by distance and then computing the advisory based on that.
But you could have a slow close and a fast coming in.
Yeah.
That's going to be the problem.
So yeah, so that kind of result, we're not going to say that that's the intended use of ACAS-XU. The other point you're raising is sensor models. So Verse is capable of defining different kinds of sensor models. So right now it's just ground truth values of these variables plus some constant error. That's the kind of results we have. But suppose you wanted to have more realistic sensor models and then verify, we could incorporate that.
So I have a question. I see how you're using Verse here. So let's assume that I'm designing a different air traffic control management system with different aircraft. Say I'm right in the design stage of cooking up. Can you give me a feel for how you use Verse? I just want to get a feel for it.
Yeah, so you would write what we call the decision logic. So right now it's ACAS-XU, but it'll be a big table or a if then else kind of a condition which says, oh, based on these relative position, these relative velocities, here is the advisory. I guess the advisory is the standard language people use, or whatever is the action that the airplanes need to take. That's the kind of if then else logic that you would write down in Python or slightly structured Python, and then it's ready to go. Yeah, so if there are other protocols that make sense to study, we'd be very interested.
One quick question. Do you need to choose discretization? Or does Verse kind of handle that for you? Just thinking along the line, I'm curious of what magnitudes of sensor noise you use. Is it like an ADS-B relevant sensor noise model? And does that affect like the computation times that you have to select discretization?
Yeah, so far the sensor noise is not very well informed sensor noise. It's sort of plus epsilon of ground truth. I don't know what epsilon value you chose, but it's not informed by actual ADS-B noise values. Yeah, but it is true that if you have larger noise and larger uncertainties in your initial set, then this reachability analysis is going to blow out.
Yeah.
And what that means is you have to partition the space that you're trying to cover more finely, and that leads to slowdown of computation. But the tool is able to do this refinement automatically. So if, for example, the system is very stable in some parts of the space, you could do like a large part of the initial condition would be covered by a single analysis like this, and you would not have to do finer partitioning. If things are blowing up, then you will have to do finer partitioning.
Got it.
And that is handled automatically.
The partition.
Yeah,
that's cool. Okay.
So,
sort of follow-up. So do you think that right-of-way rules, sort of then sort of rules can be applied sort of by layer for these two? If you find it to be right?
yeah, absolutely. Yeah. In fact, yeah. So great. Go ahead.
And then based on that, the often being done pairwise kind of sequence of pairwise conflict resolution that is happening here. So, but here it's kind of you can also handle the problem all at once rather than being pairwise. But the current practice pairwise conflict resolution. How do you think of that one? Can you also adopt this?
Correct.
Rather than having something all at once with the sequence of pairwise conflict resolution. How about that?
So what we are doing now is pairwise, but you could. So the Verse decision logic is very expressive. You could say, I want to look at the 3 aircrafts near me and make some decision based on my position relative to 3 aircrafts near me. The decision logic will allow you to write that, and we will be able to do the analysis. So that way, there is no limit on the expressive power of Verse. It is just that the protocol we decided to study is designed for this pairwise kind of analysis.
And did you find or can you that's the question that I was thinking, because the senior project and the Theodorou project that I was working on that, it was what is the limit of pairwise conflict resolution? Is there a kind of, are we going to be ending up with a sort of deadlock rather than solving pairwise rather than solving all at once?
This is outside of our expertise, right? So we are purely designing the verification algorithm. So what is feasible for actual air traffic control, protocols, and what are good protocol designs versus things that can lead to deadlocks? I don't know. So there are experts in the room who can probably comment on that much better than we can.
From the formal verification perspective, if we can get to that point of that, okay, here's the scenario. The pairwise conflict resolution.
Okay, so you're asking for something a little different. It's like designing air traffic control protocols, right? Which are good protocols versus bad protocols, and deadlocks versus things like that. So yes, verification could sort of help narrow things down by providing these analysis tools. But I would say designing protocols is a slightly different exercise from analyzing protocols, which is what we are focusing on here.
Not necessarily on designing protocols. We already have the pairwise conflict resolution, but I was wondering how much is it scalable? Based on, and then is there a situation that we can end up with deadlock, that there is no feasible solution?
Yeah, so scalability wise, I think instead of pairwise, if you go to multi-way resolution, there will not be a huge challenge. I think, yes, the formulas that internally we are dealing with using the set solvers, those are going to get a bit more complicated, but you're going to deal with 5-6 aircraft at most at a time, right? It's not going to, so it's not going to be too bad, I think. Whether we can discover deadlocks or not, That's an interesting question. So far, all the verification questions we are asking are safety questions, right? Is the separation getting violated or not? But checking whether, oh, are we in a loop of some sort? In principle, verification tools like verse can handle deadlock or liveness questions as well. We haven't done that yet, but I think that's an interesting direction.
Deadlock and disruption. And so that's going to be the interesting part, and because this is how long the trajectory is to.
How long? That's typical trajectories, like real time, yeah.
I think it's a couple thousand meter.
In terms of seconds.
In terms of seconds, currently we're doing 20 seconds.
If you guys are showing multi-vehicles and you do long trajectories such that, and this is something that's been documented in airspace with your airplanes basically had to do TCAS, right? And that disrupted the system to the point where it took the controllers the next 35 to 40 minutes to reestablish everybody's patterns, right? So you start talking about these kinds of vehicles using ACAS or whatever it is, right? Yes, you're safe, but two things happen. One, you can potentially put yourself in a path to somebody else, right? So you have this sequential pairwise reactions, right? The other one, you just completely disrupted the air traffic system that made itself lead to other things. And so the question becomes, is it something that can be added appropriately to, not so much that you're solving, new policies, but more of the demonstrating, here's the disruption that happens because I just put both of those aircraft in a path to somebody else.
Yeah.
And that may require just like the
Yeah. One thing that's not obvious to me right away is for those types of protocols, whether it has to become specific to particular airspaces, here is the storage, and because this is pretty abstract, right? This is just like 5 airplanes somewhere. But then for TCAS type of protocol, you would have to have the geometry of the airspace for a particular airfield working to this analysis, or is it?
I think you're just looking at sort of the final area where you just get a lot of airplanes coming in, potentially from different directions, trying to get into a pattern. I don't think you need the geometry to start initially, start looking at the potential disruptions. By having airplanes basically divert into each other's path as they execute these policies.
So then it should be feasible. It should be feasible to try such things.
Might be worthwhile to take a look, another graph and go, oh, you'll run this for trajectory for 20 minutes. Come back to me in 3 weeks.
No, if you're running simulation, it won't take that long. But if you're trying to verify,
how it works. But you mentioned that it's also possible in your framework to have an else project and verify that. So in order to handle sets in an else logic, between static code and
So essentially, we are not using that term in any of our papers, but basically, if you have a set coming in to a function and the function has if then else, right? Then this set can get split along different branches. And that's exactly what is getting computed. We call it the analysis tree. That
is also non-linear computation that taking place with the statements.
Okay, great question.
Values like not if this comes like that, but if something
Great question. We brushed that under the rug so far. So there are two kinds of analysis happening inside verse. One is propagating uncertainty through the if then else, and then there is the propagating of uncertainty through the dynamics. So on the dynamic side, you can have nonlinear differential equations, and we have ways of propagating those. In the if then else part, we are somewhat limited by a SAT solver that we are using. So right now we can handle linears for sure, polynomials also. But if you have very hairy nonlinear functions showing up inside the if then else, then we might have to approximate it or choose a different SAT solver. Again, we are limited by the SAT solver, not a fundamental limit of the framework.
this question. I was thinking that since you have a testing logic in there, and now we can do set-based analysis. And then you are faced with a question. Let's say you want to test for aircraft. You say that you found no obvious violations, etc., because it's not designed this way. But essentially, what you said is, okay, let's take the closest aircraft and let's do pairwise confliction. ACAS will just use the closest. So this immediately is an if statement, but precedes. So if this distance is less than the other distance, then this means that you're going to use then the neural network. So this is like an if and some very strongly non-linear part that's happening.
Right.
So I was wondering, so this, if you could tackle this kind of situation, that this means you can have a way to check decision logics that are layered with
On top.
branching statements and an ADAS avoidance protocol that's there. So you can build something that has a higher level that will provide an answer to whether a particular logic of what should I use as a rule to run an actual ADAS avoidance unit. This could potentially cover 3 aircraft, right?
Yes.
But this is predicated on being able to layer those if then else with strongly nonlinear transformation that happens.
Yeah. This is maybe at, I don't know, I don't think it's supported right now, but this is at the level of a summer project for an undergrad. I mean, it's highly doable, right? I mean, layering anything else with a neural network is just pushing more analysis inverse and then going to crown, I guess.
Yeah, I think so.
Should be highly doable. And I don't know, John, if you had more comments. So there was this branch of work we didn't present here today, given Kevin's earlier comment that we were building a decision tree approximation of the neural network. That then the whole verification could happen inside bursts. But we are not talking about that today, but John has those results as well.
There are probably, there's probably more intelligent ways to define those if statements that we could do it natively versus we're going to take probably a quick look at that summer, see if there is like a better solution that we could actually, kind of convex sense. I'm sure safety with those than else still, but at least for the purpose of this, I think the alpha crown was the more guaranteed safety solution for the purpose of this topic.
I can keep going, but I just want to make sure that we want to take away too much time for your lunch. But I'm happy to entertain while you get lunch and answer more questions. Yeah.
It's very interesting work. I understand your vision online. Right? You're not verified and then trust you don't get whatever. Or you each instance you trace a layer. Is that online verification?
Okay, yeah. So this is something we should have been clear at the beginning. This whole thing is the way we are at least pitching it is it's for design time verification, right? So you have some protocol in mind, or you've designed a air traffic management protocol, and you have some aircraft dynamics in mind, and you're offline verifying whether the protocol guarantees safety over the operating design domain, which is defined by the space of different approaches for these pairs or triplets of aircraft. Right? That's the problem we are handling right now. But there's nothing fundamental online or offline about reachability analysis, right? So if you could do reachability analysis faster, you could run it on the aircraft itself to sort of.
Online, you can start language or particular combination. Offline, the combination dynamics.
Yeah.
Angle, almost infinite band.
Yeah, so we are covering that.
So I suspect you have to do it online sometime because offline actually is no better than testing because the statement you make is I can find all the combination configuration.
Yeah, that's
right.
Okay. So maybe I should. So we are covering infinite, in fact, uncountably infinite many configuration.
And you can run the finite time. You can run 3-bit things.
Yes.
All right. Okay. I don't think of it. So essentially, you can cover the biggest stage.
Yes. Yes.
The first time.
So maybe the if there's a quick intuition I can give you, this is the actually building up on a lot of previous work that I mentioned at the first part of the talk. The basic idea was actually in this drive VR work, which is if you know the sensitivity of the system, Okay, and you can compute sensitivity, for example, the Jacobian, or getting upper bounds on the eigenvalues of the Jacobian. But if you know the sensitivity of a system, let's say it's just a nonlinear differential equation, then from a single simulation or a trajectory of the system, you can say how the neighboring trajectories are going to behave, right? That's how you go from a single trajectory or a test to infinitely many trajectories that are near that simulation. So that's at the heart of how this.
Yeah.
Yeah.
So I only need one month to done.
No, so
why do you need to do so many configurations?
because the nearness is important, right? So this nearness tells me from one simulation I can cover some neighboring trajectory.
A finite region.
Yes, a compact region.
A compact region.
Right. But then I need to cover the entire compact space, I need many of those simulations, and the balls around them will cover the whole thing.
People should would like.
Yeah.
That's good work. So it intrigues me, so I asked.
Sure.
So is the size of the patch finite?
It's a compact set, yeah. I don't know what you mean by finite, because there are infinitely many points in that, but it's a compact set. Yeah.
So you cover finite distribution or it's nearby something.
Yeah. It's a compact cover of a space, basically. That's what it is. Yeah.
So then the approaches in the different dynamic of different aircrafts, all those things can be covered. That means you can cover unknown.
Exactly. Oh, unknown, I don't know, because remember, I still need the sensitivity, right? I needed to compute the sensitivity function of the. So I need something. Yeah.
If you know, you find the sensitivity.
Yeah.
But some aircraft or some certain type of flight,
Yeah.
you might have different sensitivity.
Then yeah.
Then it's okay.
Thank you.
I didn't talk about super work, I guess. That's okay. Yeah, on the trials. Yeah, it's
Quick question. So if I remember correctly, there was a paper like a couple of years ago in NASA formal methods where it shows that the neural network compression of
this is Stanley Buck.
Yeah.
Yeah.
So were you able to uncover anything like by running verification on like that it's actually unsafe or like there is some out like, or maybe you're not using the same model, so that's why I was like, well.
Oh yeah, he was using. If I think of the same work, I don't know. There's been a lot of papers on neural network. So some people just verified the ACAS-XU without even trying to close the loop with the dynamics of the system. The work that you're referring to, I think, was having some relatively simple airplane dynamics, like Dubin's airplane kind of thing. And one of the things that he was doing was actually distilling the ACAS-XU into some quantized. And then he found that in that quantized version of the network, there was some problem.
The advisories were not just
correct. I remember that one. So yeah, we haven't done any quantization. This is like the actual network. And yes, we are trying to push to find some maybe bad scenarios where things don't work. But so far, the ones that we have found are these 4 aircraft scenarios, which is where it was not even designed to do it. So it's a little bit cheating to say I found a counterexample.
I just was curious, like, if you're using that model where was able to uncover.
Yeah, it would be interesting. So the discretized or the quantized version of ACAS should be able to handle it because it's easier in a way.
Simpler model.
Simpler model, yeah. So we have checked our results against Stanley Buck's to at least see that our simulation look the same as his simulations, just to make sure it's like a sanity check that our thing is not doing something crazy. But we haven't tried to analyze the quantized thing. Yeah, would be interesting.
Our next speaker from Georgia Tech, Akash, whom you have met through the demo today. Is more questions? Okay, Akash.
Sure. Yeah. Okay. So I just want to give a little bit more details into the Coven steering algorithm that we have been working for some time and what we just saw today morning that we demonstrated in Minihawk. So our Coven steering algorithm is an ADMM based algorithm. So it's like an operator splitting algorithm that, as I mentioned, that can handle both nonlinear dynamics and chance constraint. So I think just to give a little bit more clarity on what we are trying to do here. So I think everyone here is like familiar with mean control. So if it's like LQR or like if it's a PID or any state-based control, you are generally trying to control the mean trajectory of your system. Now, there can be systems which have process noise and state noise associated with it. And what generally happens there is you generally know a belief of where you are rather than like exactly where you are. So let's say you are at 0.005 and you have a covariance of like 0.1. Now, what we are trying to do with covariance steering is that, let's say you want to be 99% safe. So if I start anywhere in the 99%, that's like the 3 sigma envelope of your mean, I first should be able to control the trajectory using covariance steering. Secondly, the safety guarantees that we have generated are still valid. So that's the whole point of using covariance steering. So this all started from the idea of distribution steering, where you have a starting distribution and you want to move this distribution to a final distribution, which is evolving through some dynamics. Now that is a really expensive and computationally expensive process because now you have to look at higher order moments of your system. So a similar technique which came in the late 80s actually, so covariance steering's initial work was in the 80s, was to come up with just a simplified version of distribution control, which is just looking at the first 2 moments of your state and then trying to make sure that from that entire distribution, you should be able to control the trajectory. So initially, this was meant for a continuous time system because of the computational limitation that was there in the 1980s. But nowadays, like in the early 2000s, like there have been other formulations which are for discrete systems, and that's what we are using. Now, as I said, there are several variations of covariance steering out there. Some of them can handle nonlinear dynamics and nonlinear constraints. But one of the major drawback that almost all these covariance steering algorithms have is that when you have really tight safety constraints or even just normal constraints, these tend to provide very poor solutions or just become infeasible. Comparatively, our algorithm has shown that we can always get really nice solution and can also guarantee a high level of high probability of safety. And the reason we can do that is because we have like a distributional approach where we solve the covariance steering and the chance constraint problem separately, parallelly first. And what this lets the covariance steering problem does is that it can temporarily violate the constraint to get a dynamically feasible trajectory. But as soon as the algorithm converges, there are mechanisms to make sure that both of these trajectories that is generated from the covariance steering as well as from the chance constraint converges to the same trajectory. So this is an iterative process. So compared to other methods, this will give you lower cost trajectories, will generally have a higher safety level and higher feasibility. But because of the iterative process, this is going to be like a little slower than traditional methods. Sure.
About the 9% covariance, which is why it starts out large and then starts in that.
So this is a distributional control. So in general robotic scenarios, you want to start from a starting distribution and you want to take it to an end distribution, and you just want to make sure that the utmost covariance that you have is that distribution. So that would be a general scenario in robotics environment. But here we just wanted to show the full capabilities of the covariance steering, where you can actually make from one distribution, you can go to another distribution. So here what happens is if you keep running over and over, you have some trajectories which goes to all of those points because you are kind of having like a negative feedback around you kind of have a negative feedback around this region, which is going to expand and make sure that your final distribution matches what we want. But you're 100% right. In robotic scenario, we generally wanted less than or equal to. That's what we did at Minihawk. So okay, so just to give a bit more details, so let's consider like a standard quadratic minimization problem, like what we see in LQR and the stuff, where we have a quadratic cost and a quadratic state cost and a quadratic control cost. Now assume that you have some nonlinear dynamics, which has some process noise associated with it. Here, like I've written the formulation where the noise is entering through the control channel, but it's not like a strict requirement in this work. You can actually have the noise enter through the state channel as well. But for simplicity, let's assume that it's entering through the control channel. Now you know where your system is and where your system or the agent is. So you have some belief of where you are, which is represented by a Gaussian, and you have some final distribution that you want to reach. Again, represented by a Gaussian. So what we do in our algorithm is we split this into two problems: a covariance steering problem, which is trying to minimize the quadratic cost, and the other problem is trying to solve for the chance constraint problem. Then we solve a consensus problem, which makes sure that these both trajectories are coming to the same answer or some same result. And the other variables here are basically the augmented Lagrangian terms and the penalty terms associated with making sure that mechanism where this converges to the same answer. Now, the way we do this is we solve the covariance steering and the chance constraint problem parallelly. And chance constraint also is like is a projection step, so each of the step can be also parallelized. And once we have both of the solution, we solve a consensus problem to make sure that both of them are eventually coming as the same result. Then we iteratively solve this until convergence. Now this works really great if you have a linear system. But when you have a nonlinear system and you have to often relinearize so that you get the new system parameters and other dynamic-related parameters, we need to make sure that the trajectories that we are finding doesn't deviate too much from that linearization point. So in the consensus problem for nonlinear dynamics, we have a cross region constraint as well, which makes sure that the new trajectories that we are generating doesn't violate or doesn't move too far from the point where we linearized, which will make sure that the problem doesn't work. So we want that to be very close to the linearized dynamics. And then we just iteratively solve this and relinearize as we go until convergence. Now, I just want to quickly show a difference in results that you get from a traditional covariance steering solver versus like R solver. So what we're trying to do here is you have a unicycle that we want to move from this distribution to the final distribution through a narrow corridor. And we also want to guarantee that the trajectories that are generated are at least 99% safe. What ended up happening is that we tried to generate a trajectory which is 99% safe using traditional covariance steering solvers, and it was not feasible for this scenario with the noise and everything that is there. So the results you are seeing is for a reduced probability of safety of 90%. Meanwhile, our algorithm could easily find a 99% safe solution. And if you actually look at the quality of the solution as well, you can here see that the reason this is 90% safe is because the algorithm here is trying to stay longer in the starting and the ending region where it is generally safe, and trying to go really fast through the areas where there is like the tight corridors. But in practice, this is not really possible because you can't really go that fast and expect good performance there. And what will happen is if you try to increase the computational time or the computational horizon for how long you're computing it for, to be safe, the only path that the traditional solvers can take is to extend this trajectory in this direction so that it is just moving into the safe direction. It cannot find a corridor. You cannot find a trajectory through this corridor. While in our case, if you try to increase the computational time, what you get is a much finer version of this same trajectory, which is much more aggressive and controllable than the original trajectory. And I have this representation to just show why this is happening and why like us allowing for a temporary infeasibility actually makes it work well. So let's say you have a trajectory that is going, you have some points xt and xt plus 1. Now this green envelope represents all the possible points you could travel from xt plus 1 in the next time step. And because of the positions of the obstacles, the chance constraint feasible region is this between this two hyperplane. Now there can be a scenario in your optimizer step where the overlap between the dynamically feasible and the chance constraint feasible is like a null set. That means your optimizer will immediately fail because there's no feasible solution there. The solution that you see at the left from the traditional solver is when there is a small overlap between dynamics and the chance constraint, and it's just trying to solve in that direction. The reason it works well for our case is because we allow for this temporary infeasibility in, let's say, in a particular iteration of your optimizer, your dynamically feasible trajectory may not be chance constraint feasible, but eventually when it converges, the trajectory will move into like a chance constraint feasible trajectory as well. So that's the reason the temporary violation is what lets us increase our feasibility and generate like nicer solutions. Now, I just want to quickly show some hardware results that we have done at Georgia Tech with the Robotorium platform, which is essentially a differential drive robot. Let me see if I can play this. Let's see. Play option. Yeah, well.
You just go to play.
I'm going to just play it here so that then we can go back again. Okay, so what we have done here is to really check the repeatability and the robustness guarantees that we can get from these vehicles or from these algorithms. We have generated a 90% safe trajectory and initialized the robot at different starting locations around some 3 sigma and repeated this experiment like 100 times to see how many times we will actually violate the constraint or violate the safety tics. Yeah.
Sure. So what is you?
What's it?
What? So you said like you just done with the airplane problem. I don't care about the unicycle. You're using position of velocities and x. What is you?
The acceleration controls.
Acceleration.
Yes.
Here the control has full state observability.
Yes.
There is no noise in measurement.
You have noise in measurement when you're recalculating. So you have an odometry reading from which you're starting because that gives your initial belief. So there is noise there. There's noise in the initial state. But for now, for this experiment, we have not assumed measurement noise along the way.
So your plant is just a double integrator?
This one?
No.
The plane is a double integrator because we cannot have the lower level controllers of the thrust and body rate, as I was mentioning. There's an issue in the underlying autopilot which doesn't let us access those controls directly. Okay, so I think like we have enough runs of that. So we have like 10 runs of this, and I just want to quickly show how a safety violation will look like. Okay. So here are some safety violations that we have observed. So we had 3 safety violations in the 100 runs. So there is an obstacle violation here and an end constraint violation here. So with the 3 violations out of 100 runs is well within the statistics. We were aiming for a 90% safe trajectory and we were well above that. So this really shows that if you have the correct dynamics and the noise characteristics of the system, we could give really nice, robust guarantees on the controller. Now, I just want to recap what we just quickly do so that I don't have to go in. Yeah. Hit the obstacle.
But maybe actually guys.
So we are initializing at a different location. So if you look at here, right, it's like towards the corner of end of the, so that's like a 3 sigma boundary. So you are kind of like coming at the end. And the main reason why it hits is the yaw. So the noise in yaw actually affects. Like, for example, if you're rotated the other way, it takes a bit of time to turn around and come. So that's where the safety violations will come.
Yes, are you designing a U or are you designing a trajectory?
You're doing a control project. So you get a set of views and a set of gain schedules.
So you're getting a U and a trajectory, right?
Yes. A feedback and a trajectory. So you get a gain schedule as well.
The Gaussian model is sustained even if you're having a nonlinear dynamics or in that case nonlinear kinematics.
So if it is sufficiently, if the dynamics is sufficiently smooth, we have this linearization step which makes all the subproblems convex. So for what we have observed is for unicycle and like other systems which are like not that non-linear, the results like pretty much match up. But if you have something like you have done this in quadcopters, where like you have the 20 degree of freedom, that time the Gaussian estimation may not always work. So we have to do a sampling based estimation of what is your current covariance and everything. So we do a Monte Carlo sampling and try to estimate what's the current covariance and like the mean, and then try to compute the covariance steering along with that.
So it's some sort of an uncentered sort of thing, right?
Yes, but so if you had some kind of like there's a recent paper on uncentered guidance, which is basically doing similar stuff. But in uncentered guidance, you are propagating like samples of your trajectory and trying to make sure that each of the samples are controlled. But here we are making sure that the distribution, entire distribution is controlled. There in uncentered control, it is not necessary that all the intermediate trajectory is like feasible or will obey the safety guarantees. Right here, because you do for distance, there's always guarantee that will work for that distribution.
Is there a strong argument why some sort of reactive control will be superior to what you are like just open up point to some sort of thing?
So I'm not sure if there's any reactive control which is it's also distributionally.
Stay clear.
But there is noise in the system, right? So you cannot like so this is for a stochastic system. Yeah. So it's
Another question.
yeah, sure.
If you enlarge the covariance of the noise, would it be possible that in a single thing, just break and then there's no feasible path?
Yeah, exactly. So the reason we went for a 90% safe solution is because that robot is pretty noisy, and we tried for a 99% solution, but with the noise characteristics, you cannot go through that problem. See.
Okay. And currently you were achieving 93%.
Empirically, we are getting 97.
97. Thank you.
I guess one quick follow-up. So if that's the case, why not just increase the noise until the next pass?
Yes. So that is actually a way people do it. So what you do is you solve this for 90%, then use that to warm start to 99%, so that and you can slowly start increasing. You find the 95%, use that 95% to warm start. But that's like it's great if you're doing like a trajectory optimization where you have all the time to generate the controls. But here, like we want to like generate the controls fast enough too. So yeah, that's like the trade-off we have.
Okay.
Okay, so I think everyone saw the Mini-Hawk experiment. So we had the simulated online regeneration and the obstacles. So I just want to quickly touch upon some issues. So theoretically, if we had the correct dynamics, we should be able to control 99% of the distribution. That means it doesn't matter where the Mini-Hawk's ground truth is. We should be able to still control and provide safety guarantees. Which what that translates to is that the trajectory that the Mini-Hawk actually flies is always inside the covariance bounds, which is the green tubes. Now you can see that there are some locations like here and here where it is not actually inside that bound. And that's mainly because of this model mismatch and everything that we were talking in the morning. So the autopilot stack does not allow for like lower level controls. So we are kind of using like a 3D point mass model, and we have tuned it well to track so that the Mini-Hawk tracks it well. but like there are some places where you can see violations like what we saw. The second thing is, as I said, like our current implementation is a little computationally and memory heavy. And it's primarily due to the fact that we have written it in CVX, and this is like an STP problem, so it takes a little bit of translation. We have almost finished re-implementing this in like a traditional, in a lower level mosaic solver, which is supposed to make it much more memory efficient and computationally efficient. But it's like we still have to test it. It's not a direct, straightforward process because we have to reformulate some of our problems into like cone problems. Then the last thing I want to touch upon is like the computational time and the tuning. So here, like the feasibility of your solver as well as the speed of convergence is like dictated by how well the hyperparameters are tuned, or specifically the penalties of the ADMM. Now, currently, we have been tuning this manually based on like the environment, and this seems to be tedious because like as the environment change, you kind of have to retune the hyperparameters, and we have seen that you get the best results when you can change the penalties over every iterations, which is not really possible if you're manually tuning it. So on that note, we have some future work. So I think like Dr. Theodorou have talked about deep unfolding before, but I'll just give a quick overview. So the whole idea of deep unfolding is that if you have like an iterative optimization step or anything, like for example, if you have an iterative optimization algorithm, we are unrolling the steps of the optimizer and trying to learn the parameters that influence the optimizer. Basically, they learn the parameters in like a supervised learning fashion. So we'll have a training loss which tells you how well the optimizer did or computed, or did there was a feasibility or there's a constant satisfaction or whatever is your criteria. And now we want to learn these parameters so that we can generalize it to other optimization problems. So what deep unfolding provides is like a functional representation of like your optimization problem. Now, with a functional representation, basically that lets us have like better interpretability. We can look into the working of the optimizer and understand what parameters affect what solutions and how they are affecting. And this is how we go about like coming up with generalization bounds and come to certifying the performance of these optimizers. Now, the figures and the results that you see here are from. But it's like from a previous work from our lab. Some of our lab mates have worked on this. So this is deep unfolding for quadratic programs. And what you're seeing here is not sure why this is very blurry, but what you're seeing here is a comparison of a deep unfolded QP, which is the deep QP, which are these two red lines, and compare that to the state-of-the-art QP solver, which is OSQP. So as you can see here, that the deep unfolded QP actually converges much faster than the state-of-the-art QP solvers. Now, this fast convergence and you can see the measure that we are doing is optimality gap. So we can also, what we are getting here is like fast convergence and better feasibility compared to like traditional optimization counterparts. So the idea here is, now that we have this QP implementation and we have this recent paper like that has actually come up with pack-based generalization bounds, which can certify the performance of these optimizers certify the optimizer and the quality of the solution when you're given an unknown QP. That is, if you try to solve a QP that you have never shown the QP before, our lab mates were able to get some generalization bounds and were able to certify the performance of the optimizer in that way. So the same idea, we want to extend it to covariance steering, where we want to like try to unroll the covariance steering step and try to learn the parameters so that we can do the convergence and like the feasibility, better feasibility, and in a faster manner. So that's one work. Sure.
performance of the optimizer. So, in fact, kind of a misnomer. You're not certified of the optimizer. Certified the performance of the peak unfolded.
Yes.
Okay.
Yeah, so you're kind of certifying a lower bound on the quality of the solution that you can get from the optimizer. If you're giving it a problem that it has never seen before, like not trained on, basically. Okay, so that's one future work. The other future work we are currently working on is to replace the standard ADMM scheme in covalent steering with the Bregman version. So what that means is, like in standard ADMM, your penalties are applied to the L2 norm between the consensus and your problem variable. We just replace that with the KL divergence between your consensus distribution and your problem distribution. So the initial, again, this is possible. Again, the result from the paper shows that the Bregman ADMM actually converges much faster than regular ADMM, and we have an implementation of covalent steering with the Bregman ADMM. Our preliminary results show that although in some scenarios it does converge faster, the regular ADMM still gives much nicer or much lower cost. So that's some of the future work. Both of these work should be able to make the algorithm much faster, and it enables us to use this in an MPC kind of fashion, which is like the ultimate goal, so that we can correct for moving obstacles and other disturbances which are continuously changing. And that's all I have for today. I'm happy to take any questions.
I'm not an expert, but in the very beginning of your presentation, I had one question in mind. Have you thought about using diffusion models?
Yes, so that would come in the complete density. So we have previous work from our lab which have done distribution matching or density control using Schrodinger bridge and stuff like that. So that's when you have a starting distribution and you want to move to a distribution, and you want to make sure that you're moving the entire distribution, not just a couple of moments. And you're right, we can use diffusion for that, and there are other people that have worked on that similar area.
Okay, so I guess my quick follow-up on that is, if it's possible to use diffusion models, there are ways to accelerate the development process?
Yes. I'm not like a diffusion, but we have work from our previous lab which have used concepts from optimal control to make this diffusion process much faster and have a conditional depends on the dynamics and everything. So it's generally diffusion models are used for either doing some image to image or some kind of distributional transforms. Yes, but you're right, you can modify it to use it for control trajectories. It's just you just have to. It's a little bit more advanced than doing it for dynamics because you have to condition to all dynamics.
Okay, yeah, I guess we can discuss it.
Conceptual question. So do I need to know any probability to do covariance scaling? What I mean by that is, if you use the walled garden of linear system with Gaussian noise, then you can write down the dynamics of the mean and the covariance as a deterministic ODE where the parameters of the covariance are evolving over time.
Yes.
And then what you want to do is minimize the covariance or at least meet some constraints on the covariance so that doesn't hit the positive.
Yeah.
So if I approach it that way, what will I miss out? If you use the language of probability.
I think that's exactly what is happening underneath also. So even now, the covalent steering part, when you linearize and make the linear system, right? You are propagating using your standard deterministic equations. So the only thing you need to know that is you have to do a system ID on the system and find out what is the process noise or the approximate process noise. And then these solutions come from a Riccati equation of that equation, and the feedbacks come from that. So yeah, 100% right about that.
So in these slides, so ADMM is just an effort to solve centralized problem in a distributed fashion.
Yes, yeah, it's a way to split your problem and solve it. Yeah.
So usually any event should converge to the centralized solution. So why are you converging to a lower cost trajectory when you use one method of the?
So it will converge to the exact same solution if all the parameters are the same. But for the Bregman ADMM, like the tuning parameters are different from regular ADMM. So these are tuned to best of their abilities. So yes, you are right that if it was the same parameters, you should technically come to the same point. But what will happen here is you would come to different steady states. Like your optimizer will like flatten out at different levels. So that's what I meant by preliminary analysis. So what we saw is, yes, the Bregman converges faster, but like the regular ADMM can go at a lower cost and like flatten out.
And how do you choose the parameters?
Right, that's why right now we are manually tuning it. So we are working on the deep unfolding to like kind of learn the parameters so that we can just put a new environment and we can get the penalties.
It's, well, since Chuchu is not presenting, we have an idea here of having our students who are involved in this project give us some remarks about what they learned and how they feel about this whole project. So if they can come up here, the students involved, and give us some remarks, would be great.
And I want to still from you guys, I just want to say that it's been definitely a learning experience for the students, but also still a learning experience for us at the high level to anticipate like the kinds of difficulties that you face whenever you have to deal with real systems and implementations. And I just want you guys to know that we really appreciate all the effort that you put in there to not just do the experiments, but also ensure that they are going to happen reliably in front of this audience, because you don't make it second chances in these kinds of occasions. And it definitely took a lot of effort for you guys to deploy those real systems in front of people in real life, and not just show videos. As we know today, like videos cannot be rendered like that's I guess we can all trust our eyes that what we saw actually happens in practice, and we read it.
This was a really great opportunity. Like we collaborated with primarily with Georgia Tech guys, and like Akash was very helpful. Usually we deal with like perception or planning algorithms, but this was like getting to know more about controls and more deeper about like how coherent steering works and having real-time implementation on board. That was a really good learning. Like whatever capabilities that we have, we just went more deeper into it, and like it was a really good learning opportunity in that sense.
Then you were frustrated about other than myself.
I mean, we can probably move to PX4 because like we have been modifying the autopilot stack, and like initially we planned to use the thrust and body weight, which have been much more nicer. But I guess these are just new learning. I guess we can delve into implementing
the technical side, however, like every collaboration, how everything worked out, and how you had to communicate.
Well, it was more about aligning expectations. Initially, we weren't really planning on. We were more focused on implementing it on a vehicle that has like more battery capacity, perhaps. Like no complaints, like perhaps.
Yeah, I think it was a nice collaboration. Like the communication and everything was great. It's just like as yeah no as Pratik was saying, it's like there is a lot of expectation difference when you're like working on when you're working on these kind of projects, because like I think you can correct me if I'm wrong, like most of the control scenarios or the jet trajectories that you are more familiar with are like either position based or like more higher level. And from our lab, we are more used to like lower level controllers and like now not like having actual, so coming to like the UAV space where like, you have these all these autopilot systems like autopilot and everything. And they are again made sure that they work very robustly and made to work for the general public. So adding something like a lower level controller to such a stack, it itself is a challenging, and that's primarily the reason we had to, like as Pratik was saying, we had to go for the linear model, because we had all the dynamics and the setup to run the full dynamics. It's just that it's really a little bit frustrating that like, the autopilot system cannot handle it. And I think Pratik reached out to the original developers of the autopilot, and even they were unsure how to do it. So because it's been years in development, and people just don't know how to do it. So that I would say that was like a bit of frustrating part. Other than that,
initially, like we weren't really aligned with that. Like we were trying to see if we can figure that part on our own. But since then that worked out, like we realigned the expectations and like we made the current linear system demo work. Since they have their setup on, we haven't tested that for VTOLs. They have their setup for quad rotors.
And you can basically access even the direct motors. So we have Cohen steering models which are directly giving motor signals. So you are giving like PWM value directly to the motors, and there is feedback applied to that. So it's like as low as it can go.
As an undergraduate working with the graduates.
Yeah, well, I mean, even after 2 years being here,
Wow.
I'm still like out of my depth, really. Something they don't teach you in like any of your undergraduate classes is actually implementing something that you've designed in real life. That's something that you have to just do, and either through like research or through work. That's just something you have to learn in the field. So I've been very lucky to have great mentors in both Pratik here and Steve and Christos, basically all helping me out as I help them. So I think it's great working with grad students.
I think another great thing that you figure out only with this kind of experience is taking decisions. And I was commenting about that earlier. Some of taking decisions in the field that have to encompass expectations of other people and things that have to somehow respect other people's time as well, but also deadlines. And this is managing too many things all at once and still being able to come up with a good outcome for the team. So this is, if you have to work as part of the team, you can't get out there and say, oh, I need this result to happen today because I have a deadline, because we might end up destroying the system, and then this will take back the progress for some other people. Or you cannot expect also everybody on the team to be out there with you for the entire day. And so this kind of planning, decision making that respects the collaborative process and any kind of constraint that you have in the field and how we can tackle with them. Those are things that you actually have to experience and have to take decisions in that kind of mental mindset. This is a good experience for anybody who's going to eventually go out and do greater things than being a part of research group.
First of all, great job with the demo. It was really impressive. And sort of building on what Christopher was saying, if you were to sort of imagine doing this over and over again, and maybe for even more complicated projects and bigger teams, can you start to imagine how the process itself will be improved with tools, formal or otherwise?
I would say like one of the one of the major advantage that we had in the last phase of this thing is having like a really nice simulator, like a nice software in the loop simulator. We earlier had a gazebo version which was not the greatest. So I would say like most of the work to take it to like next level or like other work is mostly like checking like having a better integration of the tools and like having like a better data collection and logging systems, because right now yeah we are using ROS bags and everything which works for most of the things, but like once you have like perception coming in and you can actually have like your perception stack is spitting out like actual data, not just images. um, and when these things are influencing like your autopilot system and your controllers, I think we would probably need some kind of nicer analysis tool to see how it's actually affecting the system, what kind of what kind of these subsystems are like interacting and everything. So, which is not a little out of scope for like from like I would say like from academic group point of view, like because there's a big verification. But I think that a bit more of tools and integration is a good next step, like
I go for it. Adding to that, essentially, knowing which platform you are targeting and tailoring your expectations like for that particular system as well, because initially we like as Akash mentioned, like they're moving to more efficient implementation, but just keeping in mind that we have to have all the final version of algorithm working on a very small board which has limited computations. Yeah, that's something that we could have had handled better.
What I wanted to say was that if you want to take things like at the one step higher in terms of professionalism, what we should be thinking about is to have continuous integration pipelines where there's the digital twins of the systems that we're testing on, such that any kind of new commits and pushes to the pipelines that we test are getting systematically evaluated in simulation, and it is necessary for those, of course, to have the supporting digital twin simulations that are accurate enough and that cover the entire set of scenarios that we might think that we want to be operating under. And this is what, as mentioned also, that lately we figured out that there exists also a very good simulation environment, and that has been a major supporting factor for us being able to integrate better, develop better for those field tests. So this should perhaps be one of the next things that we start doing, that develop this backbone of continuous integration with software in the loop and digital twin simulation for any kind of push to the pipelines.
You go the way as Lockheed Martin set up their process. I remember that's great. Lockheed Martin set up their process of how they got into it. There's a step of 4 processes that they went through.
Yes. I mean, you need to go through it. It's something that we.
I'm just wondering, but at the university, you want to go faster, maybe.
Yes. I don't know how to.
Yeah.
What do you guys think?
Yeah, 100% agree. Yeah, I mean, agreement with all of those things. Yeah, real flight. So with the real flight simulation, the trajectories were almost identical to the ones that we had in the demo.
Yeah, essentially having a real flight simulator doesn't allow you to, for example, massively parallelize simulations.
That's true.
Perhaps if we have very powerful GPU platforms with ILACs, then that kind of massive parallelization of multiple testing scenarios, but we do need a
more
twin that's more accurate,
more realistic lift and drag.
Also, to get that simulator, and that, of course, requires a lot of effort to set this up as a pipeline, integration pipeline.
which you guys will find useful. Don't correct me, that's not your experience, which you guys seen, but keep building on this. Keep, every project you've added new functionality, which you have your backbone on which you need. And next thing you know, you will actually develop something that's pretty sophisticated. I've seen enough, being a grad student at some point. So, right, we care about don't graduate. I don't care how good the code is. I don't care if somebody else can use it. Somebody else comes in and then trying to dig into your code. They're like, I have no idea what you're doing. I'm going to write my own. And unless, and I mean, that's say you want to get stuff done faster, but part of the lab is no, we have a set of tools that we're going to keep building on, and that involves maybe a little bit extra with it. But in the long run, you actually end up with much greater capabilities. It's things like, it's a configuration control. I mean, it doesn't mean you're using clear case to document things to death, because it's, safety critical.
But it knows a lot.
Right. But it's like, it's.
You're asking him to document things.
But I mean, I'm thinking like, we use GitLab, right? We have configuration control because somebody's developing this branch, somebody else is developing that branch. You have to merge it into the master. Because that way you can work stuff in parallel. I mean, those are pretty simple practices. It's just that initially maybe it'll take a month to figure this out, right? But once it's set up, I mean, somebody like me in neophyte's like, oh, one second, I want to play with this simulation. How do I set up GitLab? Okay, here's the documentation. How do I, download it and copy and blah, blah, blah. Here it is. I mean, it took me a couple hours, right? Nobody else had to pull me in. It took the guy who was responsible for a master branch probably half a day, right? But then again, somebody else is using it. It's like, hey, this is no longer true, or hey, so it's almost like a self-regenerating process if you enforce it. But it becomes almost like a nature, it's culture of the lab.
Right.
And I think
I guess
already there.
Akash can tell how easy it was for him to replicate the repo, I guess, that Chris has created.
Exactly.
Yeah.
Right. It's the repo, and you just keep moving along. And I think, again, from everything I've talked to you guys about what you're planning, I think you just keep going, get there.
You want to any comments to make regarding constant plugins with requests?
Well, that's actually helpful.
Everything means everywhere, wikis.
That's actually helpful because since we are always working on different projects, if I come back to the same project after 15 days, even I don't know what commands to run. Yeah, so I have this is always helpful. There have been times I'll be like, okay, at the end of the day, I'll make the documentation, but I never do. But then I get a text from you and I'm like, okay, let's do that.
I actually have a great example of something where we've built a tool that with a little bit of extra effort saves us so much time in the long run. And it's when we were first doing these tests with the Mini Hawk, we were out there plugging in every single waypoint in a GUI and having to type in 005, go to this position. And Pratik had the great idea oh, why don't we just put this all in one script and we'd make it so much easier. And, he spent a little bit of time on that and it saved us much more time in the field.
You don't want to be over there. You used to be able to be probably something higher than
right.
It's amazing how easy it is to, I'm going to change this one tiny thing in a file because it works. Changed it. Well, that didn't work. I'm going to change it back. The file is no longer working. Sorry, personal experience. Something. And so that's where you learn the importance of configuration control. No, you don't change something in that file. I'll get it fast.
Right.
It becomes the next version, so you can really improve that.
Yeah, ROS has been a really great tool for that. We can have parameters change on the fly.
So in the big scheme of things, when you graduate, where your career trajectory heads will be very important for you personally, obviously, but if you come to industry, we often care less about what your research was on. It's more about what you learned. And these experiences that you've done here have trained you to be, how to do quality, how to do safety, right? These kinds of things, and how to advance technology. You'll find that, you know, some of this work may not transition anywhere, right? But nonetheless, it's very valuable. You know, the teaching part of it, that's very important.
Managing accreditations, managing risks, like managing those things.
Kevin, you have offers from them right now?
Yeah.
I appreciate it.
Unfortunately, so you gotta be a US citizen. But we are hiring.
But it's also about the way that your thinking process goes, gets triggered by some hard reality, and then you figure out something different, and that part conditions you to think very differently. As Sayan says, it's not just the math. Of course, you know the math, but if you go in a different direction because of this trigger, you still have the tools that you developed here, which may not find an application. It wouldn't, but it's the way that your thinking becomes more agile. And that's the important part, I think, in this experience. If I may offer one thing before I want to address it, and this goes to all the students, what I suspect you will find, even if you were inclined to be in academia in that industry, or even a theoretician, is that invariably applications uncover holes, and that usually leads you to rethink the theory and leads to better theory. A very productive, enriched theoretical development. So it's not just, am I going to strictly apply things in industry, but also in academia. And but as I said, I've seen this kind of watching and working with academia for the past 4 years that I care to admit. But it has been really, really important. But to add to what Irene said is exactly, I mean, okay, you can have a totally theoretical problem, and that's good exercise for your mind, your brain. But if you, the more challenging and the more rewarding successes in solving problems is taking some reality that's stuck somewhere and solving it, and then thinking how theoretically you could prove that you did the right thing. Because then that brings you to a different direction, both in theory, but also opens up a new horizon for applying to reality again. So in academia, we tend to solve more theoretical. Those are easier in a way, because they don't have to answer to reality. But if you can bring it in and try to justify it through theoretical analysis, which you can do with these students, then I think that's the most satisfying, because then that's ready for application. You see it on hope. I'm going to steal that phrase now from now on. Answer to reality. I like it. No, it's fantastic. It's really like this phrase. I found, like, I did the thesis because reality had nothing to do with what I did. And this is how I think, if we're going to make progress, is to think how we can improve reality. And then use our brains with the theory that we have been taught to adapt it to that, not adapting a solution to a problem, a problem to a solution, but figuring out, and that's where you really strain your brain, then when you get the answer, it's really long.
Yeah, maybe one note, because we have a team working on the full autonomy stack at Wing with many PhDs, and the folks who do really well at Wing are those who have that deep technical depth in a particular research area and know when not to use it. So they know so much and they have so much expertise that they know the very simple, easy solution is the way to go in this particular business challenge that we're facing. But then there's those moments that come sporadically when they do need to reach deep into that theoretical knowledge to solve a very specific business problem. And I'm just keying off what you were saying. I get like goosebumps because I'm thinking about specific memories of that. And knowing how to come around and know simple solution. Oh no, today for this, I have to reach deep into research right now or adapt to what's happened in the last 5 years, because a lot of the folks have been out of academia for 10 years and their knowledge is stale, but they can quickly ramp up on what's happening right now. So
It's also we can follow almost a 6 steps of the approach a problem.
Yes.
When you do this, and intuition, what's intuition? Intuition comes from a lot of training like that and experience. Then you look at a problem, as you said, you can immediately assess whether you need the more deep, the deeper kind of theory or the simpler one. And the key is actually it's always to look for something simpler, which elaborate theory might give you, but then you can sort of follow the structure of it, the core of it, and get the simple implementation. And that's what really will give you success. And not to get bogged down with a lot of stuff. I have an example that was given by one of my students at the National Technical, that happened, National Technical University of Athens, when I taught for a while. And, you know, I mean, you can prove, and sorry if people are not familiar with Kalman filtering, but you can prove that, you know, the Kalman filter in like 2 lines. And one of the students came and said, "Oh, are you sure this is true? I mean, you participate. Fine. Let's troubleshoot." Oh, because my professor used 2 pages for it. So it's not the deltas and the epsilons and stuff. It's the big picture and the simpler thing that is still robust, that you can synthesize.
Thank you for your very last.
Excellent.
All right. So, Ray, you want to talk now or you want to talk at the end?
Oh,
Have two more.
Do we have 2 more talks? Oh, 2 more students.
No, 2 more
2 more.
talks.
Let's do the second one, right? This one, yeah. I do have the question. Okay, great. Do we have like a pointer? Just the pointer? No, maybe you need to use. Just use the thing. Okay. We're doing this for my question.
So, yeah. Okay, so this is a talk by, well, from work with Professor Salapaka, and Salar will be presenting. All right, Salar.
Yeah, thank you very much. It's a pleasure to be here. I'm going to discuss network logistics and planning problems in airspace management. And today specifically, we're going to talk about AI for parameter sequential decision-making problems and how we specifically scale up algorithms using machine learning. This is in collaboration with my colleague Dhananjay, and I'm presenting on behalf of Professor Salapaka. And I want to thank the National Center for Supercomputing Applications for giving us access to Delta AI to use and deploy machine learning models and use deploy the data and everything else. So this is actually my 2nd time presenting at NASA ULI. So hopefully I have experience what kind of questions are coming along the way or what kind of ambiguities might come up. So I want to address those in the first 2 slides. So we're working at the TC4. We're working at a network level, right? We're not discussing individual drones or individual aircrafts, how they should be controlled. And we're not imposing any structure on the communication protocols or anything. At a network level, we're abstracting out planning and logistics problem to minimize some sort of a cost or satisfy constraints that are imposed on the network, right? So for example, we're talking about the optimal facility location or shared airspace design and path planning for the network and not the individual drones. So we actually come with the assumption that all the other technical challenges have been satisfied. So now we are at the network level, right? And the second thing is the problem that we discuss here are combinatorial. So we have a bunch of objective functions combined together, and this makes the problems NP-hard. So I'm not only talking about path planning or routing. This is in combination with another cost function, and these two form a mixed integer problem, right? That we have to discuss under some constraint. For example, the first problem is routing plus the resource allocation problems, right? These two cost functions have to be satisfied simultaneously and jointly under some constraints. And this makes it much harder than actually tackling one of the objectives when you want to solve them jointly. Or if you want to do routing plus scheduling or congestion aware scheduling, we have, and I will discuss some of these problems as surveillance and certain sensor covering, as well as small cell network problem. So in our previous talks, actually we have discussed our framework, how it comes with sensitivity analysis, capacity constraints, how we incorporate obstacle avoidance, again, at a network level, and robustness. But today I'm going to mostly discuss AI for scalability and network dynamics. So we use a framework for parametric sequential decision-making problems, which is a stage-wise framework that actually deals with two types of variables. One variable are the binary decision variables that we relax to probability distributions that correspond to the stochastic policy that the agents need to take in the network. And the second set of parameters are these parameters showing alongside nodes, this y1, y2. These are the continuous set of variables that correspond to some variable that we want to optimize. For example, for the FLPO problem, which is the facility location and path planning, the path actually corresponds to these variables, which are binary variables, and then the optimal location of the nodes or the facilities are actually these continuous parameters. The framework we use, actually we take different concepts from different branches. For example, of science, for example, from information theory, we actually use the maximum entropy principle and another aspect of it to actually balance exploration versus exploitation. From control theory, we use control Lyapunov function and control barrier function to actually account for obstacle avoidance, and we replace gradient descent with that. From optimization theory, we have used dynamic programming to build the solution I want to show in a few slides. And from machine learning aspects, we have done supervised and reinforcement learning with different policy optimization methods on different architectures to actually do the scaling up. Details coming. So again, these problems are NP-hard, non-convex, non-smooth. They have many local optima, and the search space is extremely large. The three problems that we have actually shown the results for in our previous talks are these three problems that we have solved for small to moderate scale networks. The first one, like I said, is the objective is to optimally route a fleet of UAVs on a network of nodes, and to find the optimal location of the nodes at the same time, such that obstacles are avoided and battery constraint and energy constraints are satisfied. The second problem we discussed was that now that the nodes are fixed, how do you route the vehicles, and how do you schedule them on the nodes so that there's no congestion or other type of constraints are satisfied? And they're all we have used the same framework for all of them. And the third one was the routes are fixed, the nodes are fixed. How do you schedule such that some other constraints are satisfied? For example, the precedence order
congestion constraint and processing time constraints and those kind of things. Today, I'm going to specifically focus on this problem, the first problem, and I will explain it more. So this is an example of the paper that I had the link here. It's not showing here. This paper, so this is a solution, for example, we have. There are a set of obstacles in the environment, and these blue dots, they correspond to the charging facilities. For example, I can show in the next slide. Oh, this picture. This is, for example, our work with crystals, where facilities in this case are these marsupials that can provide some sort of charging and maybe other services. They can do. They can be any facilities, right? So the goal is to optimally find an optimal location within the network and also route the vehicles through these nodes such that the obstacles are avoided. For example, the facilities cannot be at the location of obstacles and the routes cannot actually go through the obstacles. We did benchmark actually. What we do, if I want to briefly explain the theory behind it. So if the original cost function is this term D, which is simply the total route cost for the drones through the network to reach their destination, we don't solve D directly, this cost function, we add the Shannon entropy term, right? And we can and we work with the free energy function. This is the form of free energy function, and this 1/beta is actually the temperature, right? The temperature parameter. So if we control this at very low beta, what happens is the policy will become as stochastic as possible, and you actually convexify the problem using, if you look at this figure here. So it's a convex approximation of the problem, and if you increase beta to infinity, you converge to the original problem D, right? But you do this through a process of annealing, and this helps us a lot with removing a lot of parameters, because when you actually use this form of cost function, you get the explicit formula expression for the stochastic policy terms, and this is the Gibbs distribution, right? Remember this form of this Gibbs distribution, because I'm going to come back at this when I'm explaining the AI part. And when we did the benchmark with other optimizations that actually, other algorithms that are usually used in the literature to solve this sort of combinatorial optimization problems, we had gained a lot of speed over them, and the cost was much orders of magnitude better, because we have just removed those set of variables, and the free energy can be explicitly shown only via the continuous parameters that we need to solve for. And in our case, the continuous variables are the locations of these facilities, right? But there is still a problem. Our problem bottlenecks at when we want to optimize for the location of these facilities, right? That is still a problem when there is a lot of them, right? So even the actually evaluation of the free energy itself can grow exponentially if you have a lot of these facilities. So the bottleneck of our algorithm happens not at when we want to get the policies, but but when we want to actually solve for the continuous variables that correspond, for example, in this problem, correspond to these facilities, locations. Right, so we have to solve that if you want to solve the scalability problem. Oh, these are the initial deployment of the UAVs. They have to go through these nodes to reach a destination. And if you have if the number of these facilities is very large, like you can think of it no longer as a facility location problem, but as a shared airspace design problem, because you can think of these nodes as the set of spatial nodes that you design, that these nodes, that these drones can fly actually through these nodes and reach different destinations. I will show results for that.
So for that part, we have to offload the computation to a learning module, right? There are some challenges with it. For example, there's varying sizes of inputs and outputs, right? And it has to be adaptable to include different kinds of constraints. And more importantly, getting true labels for supervised learning is costly, because if you want true labels, you have to solve the optimization problems and you have to have the solution for it. But it's for large instances, sometimes it's not even feasible. So, but if you have this, it will be very useful for our application, because you can have fast approximate solutions instead of slow exact solutions. And we prefer that. And we don't need to rerun the solver whenever something is changed in the network. We just have to do another inference on the machine learning part. And one other thing is, or maybe I'll explain that in the next slides. Now, when we want to solve for the continuous variables, actually once we have the gradients, that also solving for the parameter itself when you have the gradient is also not the problem, because that could be really fast. This is the parallel work in our group that we're doing, right? Because we use the free energy, we can use the free energy as the Lyapunov function, and instead of solving the gradient, instead of doing gradient descent, we can just look at this quadratic program, right, to solve the control U, such that the free energy function over these of these parameters is actually lowered down. So this part, what I'm saying is also not the time-taking part of the problem, because this quadratic problem can be solved very fast. Getting the gradient is the problem. So we want to address that. And one thing is, so you can, one way to look at it, we don't like the solutions that you say, okay, there is this black box AI module that there is the input nodes and there is some desired output. Just feed it you have billions of parameters, right? Sorry, millions of parameters, right? Unless you're ChatGPT, but you actually feed it all of these inputs and you expect to get the desired output. We know the structure of our solution and we know what to expect, right? We know we have gained a lot from the free energy function, and this annealing concept that we have for the small and moderate size networks. We don't want to lose that structure. We want the AI solution to also have the same structure. So we have actually shown. I won't go into too deep into the theory of it, but the free energy can actually be approximated at any temperature value if you have the free energy value at very low temperature and at very high temperature. Okay. So if you have a module, this log free energy is just a log sum exponential function over all of the set of distances that your for all the set of distances that your drone can have to reach the destination. This m number of these, where m is factorially large. It's if you have it, then free energy is just a approximation of the min function, right? It's just a soft min. So if you can approximate it like that, so this module takes the temperature and so what you need, and the free energy at very high beta is only the minimum of all those these. So it's the shortest path. So if you have the shortest path, you can, through this network, right? Through the shortest path network, then you can feed it to this log sum exponential approximator and get the free energy. Once you have the free energy, getting the gradients is easy because this is all happening inside the computation graph of the modules, and we have the actual expression for the gradients of those. So closing the loop and solving for the continuous variables becomes much easier. So what you need is a shortest path network and this network. So we actually train these two networks, and once we have it, we have a good solution for getting the gradients of the free energy with respect to the parameters that we want. And this shortest path network, what it takes is the start and end coordinates of all the drones. And also the parameters here is the location of the spatial nodes and a set of constraints. And what it outputs, in our case, it outputs the stochastic policy, which you can interpret as giving you the set of possible distances to take to your destination. Please.
In that scenario where rover want like that stochastic nature helps with the problem. For example, like you want your distance to be spread apart, like, or like you want the parameters to explore and all these things.
Yeah. So the biggest benefit that this gives you is actually it makes it insensitive to the initial initial conditions of your problem, because since you're solving a combinatorial problem, you can always treat it as, okay, I'll solve this and then use the solution to solve the other. But how do you initialize, right? That is not a problem when you start with very low beta. That means you're beginning with the biggest stochasticity possible in the problem, and you track the solution by increasing beta over time. So you always keep track of the optimal location and use the location of use the variables from previous beta as your new solution. So that is the main benefit that's coming. So you need the control level of stochasticity in your solution. Yeah. So this so we need an approximator for the shortest path. So we need a shortest path network. What we have used is a modified transformer architecture. By modified, I mean we have modified the attention modules. We wanted to be able to do real time. So many of the shortest path algorithms that you see there, they have this dynamic programming assumption where you have to solve the entire route in order to understand what is the next best step I should take. So you should solve the entire thing. But when you have the shortest path, when you have a machine learning module for that, you don't need to have it. Just given the current step and the state of all the other spatial nodes and drones, what is the next best step, or what is the next best K steps I can take? So it's a K hub. You can do that, and it's very useful. So in many cases, you don't need to solve the entire route for the drones. We have made instead of the quadratic attention that there exists in the transformer architecture, we've made the inductive attention module, which is linear. We have shown that it scales linear with the number of parameters that we have, which is quite useful. And also, imposing constraints on the set of spatial nodes becomes much easier when you use attention, because you just mask out the nodes that you don't like, right? And remember the expression of Gibbs distribution I showed you? This is actually the formula for what's happening inside attention. And we have modified it, right? We have added this beta value, and we have injected this bias term that the network no longer needs to find out or learn that there is a geometric distance between the nodes, and if you inject it, it will become easier for the network to learn. So what I'm saying is the attention formula has a very natural way for us to integrate our own Gibbs distribution and our structure of the solution. And I've shown this in the simulation part. For small networks, it's not very notable, but for when you increase the size of the network, this blue line here is when you have injected the structure of the Gibbs distribution to the attention line. So you see that learning has become much easier for the encoder of the transformer without losing anything on time here in this chart. Yeah, and this in these charts, actually the gray line is evaluation of the explicit formula we have for the stochastic policies. You see the problem when the network size becomes big. And this is just evaluating a function. But if you use the shortest path network, if you use the machine learning module, which is also comes with the benefit of being parallelizable, so you can do it across all of the drones at the same time because it's just the same set of instructions that you can just run on the GPU for all the set of drones. So we become exponentially faster than our previous solution. We can do the k-hop prediction, like I said, and the scaling, as you see, is here is linear. But you see up to, like, for example, 80. We've shown up to 80 number of facilities. The previous solution is faster than the machine learning solution, but the main advantage becomes if you use the big networks. And we can use the same with a small modification of the network. You can use it for different set of problems. For example, here I have used it for the sensor coverage problem, which is a form of TSP, right? The traveling salesperson. Over different varying sizes of networks. For example, here we have it for 10 set of nodes. So the goal is to for the agent to go to different nodes and collect data and come back to the initial deployment position. This is for 20. This is for 50, I guess. And here for the larger set of nodes, you can see how it's finding the optimal route across the nodes. And this is the working of the shortest path network. So given a dense graph and the start and the end deployment positions, see how it's doing one prediction at a time. That's the autoregressive inference. And the actual optimal route is shown by the the dashed green line. So see, we're always within the 5% almost rate of error with respect to the actual optimal path, but this comes with the benefit of speed and being parallelizable. So it's we take that as a win, and this is very useful for our application because we're only using this network inside our overall architecture, right? So this is the useful part. And yeah, like I said, if the number of facilities is very large, you can think of it as the shared airspace design problem, where the goal is you have a lot of set of spatial nodes that you want to design as a central aggregator, right? You want to design a set of spatial nodes such that given the deployment position and the target position of UAV fleet, you want them to travel through these spatial nodes such that they can reach the destination. And it comes with the benefit of being efficient because you compute it once and you reuse it for all. And it comes with the benefit of being predictable because you have removed a lot of redundancy in the system. And also, for our case, imposing structure, for example, for the air mobility, actually imposing structure, we can for obstacles and other set of constraints becomes easy. We just impose the temporal and spatial buffers on the design nodes, so we can control that at a network level. How the drones actually individually do it between the two nodes, that's up to other technical challenges. But at a network level, we can take care of it by imposing these buffers. And yeah, for example, so I'm here showing it for a smaller number of nodes. The goal objective here is the red dots are actually the target positions of the UAVs, and the blue dots are actually the deployment position. And the goal is to design this optimal location of this. I haven't shown the routes here, but they're being jointly solved, right? We're jointly solving the optimal location of these gray dots, which are here the facilities, and also the route of the drone. So you see, for example, in these are just the 3D views. So how they're forming this chains right? For all the UAVs to go to their destination and how they're forming their shape, their optimal location. And if you increase the number of these gray nodes, the spatial nodes for shared airspace, you see how it's evolving to the optimal solution, and using this AI architecture that I just showed. Okay, and lastly, we want to actually the future directions that we're taking is using the modified architecture that I showed you by imposing the Gibbs distribution structure on the attention mechanism. We want to include the capacity constraints and use the control barrier functions to actually account for the obstacles. And use the same, translate the same solution to the scheduling problems as well. And instead of working only with the shortest path, to get a better estimate, one other thing that we get for free if you use the machine learning module for the shortest path is you get at each time you get a stochastic policy and a distribution of so for distribution of the decisions that you can take. For example, if you solve for the shortest path and doesn't work out, you don't need to resolve the problem. You just have to sample another time from the policy, and only the better routes are more likely to be sampled. And hopefully, publish the paper and the code for the work. Yeah, that was all. I'll be happy to take your questions. Thanks.
Centralized planning, right?
Yes.
So you have to assume some level of communication.
Yes. We have assumed here. We have assumed there is perfect communication.
From just the airspace perspective, right?
Yes.
Saying, okay, it's airspace design. Right?
Yes.
What if your constraint is not the shortest path between 2 points for any UAV? What if there's some structure to the airspace? For example, there might be corridors. And so part of it becomes deploying and leaving corridors. Right. Potentially we'll also we can start looking at capacity. Right. How easy for one out to implement that?
The capacity, yeah, the capacity, the corridor. I think that's a great point. We have to address that. Right. The capacity constraints come almost for free in our framework. Because we can, if we use the same structure, then the capacity constraints, like I showed, can be easily implemented on the modified attention architecture that I showed. So, yeah, we have also demonstrated something for the moderate to small size networks with the capacity constraint. For the corridors, we have to take that into the framework eventually. I think so far I haven't thought about it carefully yet, but I think it's important.
Yeah, again, especially if you're going to start applying it to the airspace system, right? So whether future UAV is going to be flying corridors or in today's airspace, when you actually have specific lanes you have to follow.
Right.
So you don't have that freedom. And when I say capacity, let's say it's not so much capacity as a constraint, but more of if I have a corridor, one of the questions somebody would be asking once they do that kind of airspace architecture. How many UAVs or how many vehicles can I accommodate appropriately scheduled? And they start playing games of, well, what if I don't have that perfect flow, right? Somebody's going to lag.
Yes.
So all of that becomes part of your consideration.
Yeah. So actually, yeah. We have a solution for that. This third one, where the corridors are actually fixed, and in that case, the only problem becomes the scheduling of these nodes. We have done that for small to moderate scale. We haven't scaled it up yet. I only showed you scaling for the first problem. But yeah, that's actually a great point that we want to actually translate our scale solution to the other problems as well.
Because I think that's going to be very, very likely.
Right.
The story with DSP, is this in any of the papers that you mentioned, or?
Which one?
The traveling salesman. Where you said, okay, I'm doing this and it's not optimal, but it's much faster.
Yes, this one.
Yeah.
Mm-hmm.
Is this in any of the 3 papers at the end that you mentioned?
No, it's actually I think the first paper. I'm not sure if this is done using the linear transform, the modified thing. We haven't published this yet, but the original transformer was used for the TSP problem back in 2018, I guess. So this is using the same thing, but for the shorter span, I haven't seen.
Okay, because I'm kind of wondering in terms of there's many methods that approximately solve TSP without like in polynomial time, right? That are entirely non-linear based. And so I'm just kind of wondering how.
Yes. Yeah. If you read those papers, they always do this benchmark.
Yeah.
I think the fastest one is Ruby for the TSP. But this was only the baseline of the. It acted like as a baseline for what we are going to do for our framework. We just translated that solution and see how that fits to the solution that we provide for the joint optimization.
Okay.
You have it just on the right side. So your sensor covering algorithms are to find locations for your sensors in order to probably get data to minimize your energy, right?
To minimize the total travel cost.
Yeah.
Total travel distance.
And it's not related to your performance index of the energy.
Here we haven't. So in this one, right? Here only the Euclidean cost is used, the total Euclidean cost. So the actual distance. Here, as we were reading some other papers, we have here used the squared Euclidean cost, and that kind of represents energy consumption for the drones.
Yes, presenting that this is another form. If you have some form of an energy and then you try to make sure it doesn't increase, that's another implementation of your theorem. And that get to the convergence, but coming to it from a different perspective, one doesn't really think about it that way, but it's actually that theory in practice. It's the Prof theorem realized in the real system.
That's a good observation. Yes.
Yeah.
Thank you.
I'm supposed to be the next speaker, but since most of the work has been done by Hyung-Jin, I'd rather have him discuss the development of the simulation capabilities, realistic simulation capabilities that we have developed over the last 2 years, 3 years. Be online.
Yes, I'm online. Do you hear me? I am online. Can you hear us? Yes, I hear you. Do you hear me?
Hello, do you hear me?
Yes, I can hear you.
Okay, good. And slide is on.
Yeah, yeah.
Okay, so I can start now, right?
Yes, yes.
Good, good. Okay, good afternoon. So my name is Hyung-Jin. I have been working with Dr. Voulgaris as a postdoc when we start writing the proposal for this NASA ULI. Now I moved to Tennessee Tech already 2 years ago, but I've been working with Dr. Voulgaris on this topic, especially on simulation development for all these efforts. So let me briefly introduce what I've been doing so far, and also I will go over 3 works that use similar simulation environment that we developed from this effort. So when we were writing this proposal, already I see myself as a little bit aged group in whenever meeting. This movie was really impactful during my childhood, and I was very excited that we are going to make autonomous air taxi project. So, and as I think about this project more and more, what is needed is I think that it needs really good simulation environment, because for autonomous vehicle, it needs high-level perception and visual information usually has a lot of important information for autonomous driving. So that's why I spent time in developing this simulation environment. Furthermore, another thing that I realized was through the work with Dr. Christos and all the others, and it looks like we need to build a little bit bigger plane. Although it is still ongoing project, I had first takeoff just a few days ago. I have updated video in this slide. So 2 relevant work that I did with this under NASA ULI, so developing this photorealistic simulation environment, and some work in building customized RC plane that can carry small GPU. First, on simulation environment. We had several milestones starting from 2023 when we were writing proposal and also when we were announced about the grant. The first step that we did was we brought NASA's MATLAB Simulink versions of the Guam, and I combined this to car simulation environment developed by Kala project. So we had flying car, and also we had sensor and controller interface based on Roscoe Noetic. And then this version was used by Ayush in Professor Lewis group, and I think someone in NIDA's group also participated in the first AIAA SciTech paper we wrote together. So we had very simple trajectory following with this simulation environment. It is just straight line to the landing site, but the timing was using polynomial trajectory. And then next year, I incorporated a better looking vehicle, borrowing 3D model from a lot of the game development or 3D model development community. I downloaded by paying it, so I hope there's no copyright issues. And also I added this UNR's mini hawk to this Kala UA4 environment. And then around that time, Dr. Fan in MIT, she shared this Python JAX migration from MATLAB Simulink 4 Guam simulator. So it was incorporated here. And then I was able to get help by Ayush and Dr. Luisha's group. He started to put everything into Docker container so that it can be deployed to different groups. And then using the simulation environment, we had better mission or use case. It is to detect helipad. I did not use any visual inertial odometry, so the detection of helipad is purely just getting the relative position. Very simplified. So what it does is it just see the camera frame and then draw the bounding box. Then this will give you relative position from the center of this camera view, right? And also size of this bounding box can be used as additional information. So in this simple setting, we could demonstrate this helipad detection and landing while we are running this Python JAX-SQUAM vehicle dynamics in the loop. And very simple controller. And year 2025, by knowing that after Evangelos, Professor Evangelos group, they were using this AirSim Unreal 5. And also we know that the Kala is also developing Unreal 5 version. So recently we added this Kala Unreal 5 version that has this aero vehicle in it as a Docker, and it is shared to the Louis group and Professor Snyder's group. And to now I started to using more NVIDIA's assorted collection of ROS packages that is extended for GPU usage optimization. So what did NVIDIA was, it could be wrong, but that's my observation. They collected all that existing impactful ROS packages, and then they could improve this more. Why? Because if you can share the memory within GPU, not passing between CPU and GPU, then you can run Python packages, the ROS packages developed for CPU seamlessly with the GPU computation, and also the bottleneck due to loading image data into one software and to the other software, it takes time. So they did that such interfacing optimization. So I started to use this, and then my plan is, although I have very humble retort, why? Because this is a modification of the existing RT plane. We are interfacing this computation on board. We had just take off this few days ago, but we can still run some hardware in the loop with this Kala UE5, let's call it ULI simulator. Because NVIDIA is maintaining all these collected ROS packages, it is, although the original idea and original algorithm was developed by open source community, it's a better maintaining, maintain, and the compatibility is less. So my plan, already I had used this visual inertial odometry and map building using a ground vehicle. But at this point now I have hardware, just a fuselage that has all this device mounted. So my plan is to use all this 2D navigation tool first, but it has 3D map construction functions. And that's my plan to use this environment that I developed and I'm going to develop. This is already what you have seen before. This video featured the second milestone. I will play this 10 seconds. So we had this Wiscoda, and you can see that there's cars on the road, and using YOLO kind of object detector, you can do very simple landing. So latest work that I've added to this simulation environment, I already gave you the idea. What I did was I downloaded the 3D model from some game development community or web store, and then I interface it using Blender and Unreal game engines, and I can bring it to this UE5 simulation environment. So it has much better visual compared to UE4, and this vehicle is already inside, and we can interface using the same pipeline with minimal modification. So, and then another thing that I've been doing so far here at Tennis Tech is virtual vehicle development. Simply, we just want more payload to carry. It needs more modification, but carry this Destinori Nano Super. This is smaller. It is 8 GB memory, so it is less than other Destin family edge computer like AGX, but it can still handle map building. I ran this with my ground vehicle, and if I do some optimization in all this updating rates, I think I can add even object detection too, because it looks like computation needed for map building and all this visual inertial odometry is more than running very light neural network for detection. So let me move on fast. So this is the real hardware that we are making. The Ori Nano is inside here, but we did not do the USB cable or the connection. But I believe it has enough space compared to all the other platforms. You probably have seen this SNC's Voulgaris 10. So for me, maybe it is too expensive to buy something like Voulgaris 10. Even if I find the source from China, they cost easily more than $10,000. But this one is cheaper. So this is one slide that I presented some time ago. How can we use this simulator? Yeah, basically you can connect them using Ethernet cable or Wi-Fi, and then you can have the mobile GPU computer to deal with the sensor images from the simulator. I think that is actually a very crucial step, because without doing this, you cannot check the computation load. So that was planned, but never done it fully. I plan to do this. This is the another vehicle just for gaining some experience for the takeoff. We just had a takeoff, very 2 meter. But it was a takeoff. So because of a lot of crashes, now we do not even put this tail here. Now it becomes like quadcopter attached with a frame. But we are moving forward. And I think that this one truly has a payload 3 kilograms. So I'm looking forward to it. Okay, this is the real work that I've been doing so far for ULI project. I mean, up to so far. Now I want to dive into some use case of this simulation environment and also relevant simulation environment. And I want to first share the background about this. In 2023, when you are writing this proposal, this simulation environment was already maybe industry standard, especially for autonomous driving. And then NVIDIA joined in here, and they also developed their version of the simulation environment. And then nowadays, looks like almost all robotists who participate in this full-lag robot competition, they use simulation environment for training their data-driven or machine learning-based controller or task planner. And looks like almost all of the Chinese startup company worked on the humanoid, or including some Korean. They seem to use this kind of simulation environment. I believe that they are not necessarily very good at physics, but it has been with some simplified model and then with large scale, so that it can generate data or let's say optimizing using stochastic gradient. That's what we do in a lot of machine learning or reinforcement learning, right? If you have more data, then you'll have less variance in the gradient, so you can eventually get a good optimization. So that's a trend. And looking back, looks like what we studied 2023 was in line with the trend. I think that although maybe because of lack of manpower available in academia, maybe we could not surpass NVIDIA, but I think we started right thing to do. Okay. So this is one of the use cases of this simulation environment. What is it? Let me try to do everything quickly. So in short, I think that even if I can train the object detector for the landing spot, I use the real helipad images available from GitHub. It has about 5,000 images. I trained it, and looks like it is not going to work all the time because especially this image was never collected from the nighttime. So what we did was simply I ran this optimization loop. Usual, let's say this is usually called as design of experiment or Bayesian optimization. We made very simple small dimension optimization. It's nothing but data augmentation using 2 tuning knobs, the size of images, or changing brightness. And we ran through this loop for retraining of this object, the landing spot detection, and then the result is initial model. It has 50% success rate, and now we were able to improve 20%. I think that although this is a very only 20% improvement, but we show that this approach would work. So let me move on to another use case of the simulation environment. So why simulation environment can be useful? It is interesting. I think it became very interesting now because a long time ago, we were always just trying to make something most close to the real environment, right? But this approach in adversarial machine learning is a little different. You can actually use the model because we had all the model information that you can generate adversary example that is challenging to the model. Why it is possible? Because you have all the model parameters, so you can also this auto differentiation used for gradient descent algorithm for training deep neural network can also feed it, connected it to some loss function for the adversary. That means you can generate adversarial example. So what I did was the previous work has been mostly offline generation, so it was not suitable for the online attack. So I did some I added more device that enable real-time attack. So we were able to show it with the simulation environment. In normal operation, it goes to one of the car, and in with the attack and with this binary decision making, you can make. This is maybe without tag. Let me show you. Oh yeah, it is actually putting the target at the bottom yet, but you can see that it is making this. Yeah, this is perturbing. So also we show this with the real vehicle also. 1 minute is fine. I think we can watch it. So there was because of this. So assumption that we have the full parameter of the model is very strong. So using spending just 10 minutes of training, you can actually make this incorrect detection easily. So it was not pre-trained, it was a train on fly, spending 10 minutes. Why is this possible? Because we have the full parameter of the model. You can do the same thing with the autonomous car. Let me pass this. Another use case of the simulation environment is this. I think that this idea is probably came from all that nice discussion from maybe Professor Louis or Professor Evangelos. I think that they've been telling that uncertainty of the neural network can be used for controllers. So maybe borrowing simplex structures or binary decision making. So what I did was also borrowing the tool existing robots control. You can sometimes put more weight on rejecting disturbance or rejecting the noise. And in this system norm optimization, right? And using this, also I have the information of this uncertainty estimation using Young ensemble method. What this figure demonstrates is as I increase the dust level inside of this 4 simulation environment, you can see that this thin line around the thicker line actually represents the uncertainty level. You can see that this thin line box is much bigger than the other, right? And also the classification is already wrong. So as you increase the dust level, you can see this uncertainty level is increased, and then that is actually estimated from this ensemble method. That means I can use this uncertainty estimation for this switching logic. So this first line is 100% robust sensor noise robust control, and this bottom line is controller design for mostly disturbance rejection. And I didn't have time for training reinforcement learning. You can also train this threshold. I just did exhaustive testing. It looks like if I set this threshold to 15, then I can get the best terminal error reaching to the target. So this is a use case about simulation environment to show that uncertainty can be actually used in choosing better control tuning. And there's another even simple assumption is here. I switch only once. There's no behavior with it. Okay, I think I spent about 25 minutes. So thank you, Dr. Voulgaris, for this exciting opportunity. Also, thank you, Naida, for this exciting opportunity. Now I'm in Tennessee Tech, but I really like this 3-year experience that I had with this Data ULI project. Thank you. This is all I have. Yeah, I cannot hear anything. I did not hear anything actually. Did anyone
questions?
say anything?
I'm not sure the reception was so great, so maybe people don't have.
Okay.
Presentation to our group where we're discussing
I mean,
what we're doing in BAM and EM, and so we both can ask all kinds of questions. Hold on.
And we all use scripts.
Okay, good. So everybody's happy, Hyung-Jin.
Oh, really? Thank you very much. Then I hope you have a great time there, and hope to see you, all of you, again somewhere. Okay, thank you. Bye.
Okay, thanks, Hyung-Jin. Okay.
Bye.
So, all right, I think now it's time for Irene to put some remarks in, and Naira will follow.
So I'm in pre-closing remarks.
You're at NASA.
That's the NASA closing remarks. I go, nothing, no, fine. Got you, coming. So I just, I've been the technical point of contact for NASA, technical monitor for this ULI for the past 3 years. It's been a privilege working with all of you. It's been a very talented group. There's a lot been accomplished. We've asked a lot of hard questions. I want to thank the advisory board. In fact, 3 members sitting here. They've asked hard questions, and I think that just made the project better. And I wish we'll find ways for you to continue. And we certainly look forward to ingesting quite a few of your technologies into our programs and following your research in the future. So thank you very much. Appreciate all the PIs and especially all the students and postdocs that spend a lot of time and effort. And this is not the end. We have some invited sessions at SciTech 2026. So that will be our crowning glory with a full number of papers. So thank you all very much. Appreciate it.
And finally, my turn to say thank you to everyone, starting from NASA ULI leadership team. Kushik, thanks for attending and helping us with your presence, with your support. Irene for her leadership through the years. All the team members for their contributions, the advisory board, Kevin, Lena, Brandon, thanks for good feedback. Petros and Christos, thanks for hosting us. For all the arrangements with catering, with transportation, with fantastic demos. It has been really an outstanding experience. All the students and postdocs were working day and night under my tough pressure, with my tough comments, bearing up, putting up with me. I am a demanding person, no secret. And finally, thanks to your dean, who is not here now, Indira Chatterjee, for welcoming us with her morning comments yesterday morning. Thank you for taking care of the coffee and everything. Right, and the students, the exceptional driving, the transportation, I don't know, Jessica is not here. Thank you, everyone. I
have to leave.